So the first presentation that we have today is from AFL Global, and it's titled Swage Technology in Substations. And speaking on behalf of the company is Dan Baggett. Dan is a product engineering manager. He's waving at you there. Dan Baggett serves as the product engineering manager for accessories within AFL's energy group, with more than 19 years of engineering experience in the energy sector, from power generation to transmission and distribution. He brings a deep technical experience to his role. He holds a Bachelor of Science degree and an MS degree in mechanical engineering from Worcester Polytechnic Institute in Massachusetts, and oversees all technical aspects of the company's product lines. So that's the introduction, and I see if you would share your screen, Dan, that would be great, and I will put Dan's presentation into the chat.
Okay. You guys can all see my screen, correct, Randy?
Yep.
Okay. Wonderful. So thank you all for taking the time today to listen to me talk. My name is Dan. As Randy introduced me, I manage our product engineering team within our accessories subgroup within our energy market. That's going to be not only substation items we're going to talk about today, but that also includes all your transmission, distribution, motion control, all those fittings that you're used to from not only AFL, but Dawsert and Alcoa over the years. All of that is kind of morphed up into the organization we are today. Okay, so the agenda here today, we're going to talk a little bit just about the Swage technology itself, specifically or primarily for substations, and then talk a little bit about Swage grounding, which is the copper version of that used for ground grids, either on a substation or for any grounding application that's out there, be it transmission towers or other types of grounding mats. Before we kind of jump into Swage and substation itself, just understanding that AFL, we are a name that's out there. A lot of people associate it with fiber optic. We kind of brought OPGW to the United States back in the mid 80s. But the division that I'm part of, which is accessories, we've been around since the early Alcoa days. The Aluminum Company of America had an arm that did transmission lines. And they figured out very early on, can't have a transmission line if you can't hold it up in the air on the towers. So the division that I'm part of was born well over 100 years ago. In the 80s, Alcoa and Fujikura joined up together to make that OPGW. Aluminum Company of America is aluminum, and Fujikura glass fiber kind of all merged together into what that OPGW technology is today. Along with that, they kind of broke off the accessories arm from Alcoa, and that ended up with AFL, which is where I'm speaking from today in Duncan, South Carolina. This little infographic, let's see if I can do a laser pointer. There we go. So in here, you have your standard transmission towers, all your dead end structures, your suspension units, your motion control devices. All of that would fall in the transmission space. We have a handful that play in the distribution market. Fundamentally, it's the same as the transmission, just smaller cables. And then we have a large portfolio, especially as it relates to substation, to allow AFL to provide not only your standard welded components, you have typical compression, you have bolted components, and you also have Swage. Swage is a little bit newer to the electrical market. It's been around for well over 20 years. We are starting to see higher and higher utilization of Swage in substations. So before I jump to the next slide, does Zoom have like a raised hands type of deal in here?
Yeah, I'm not too sure about that. I think you should just not count on that.
Okay, so
Okay.
no hand raising in Zoom, but typically what I would jump into is just who here is familiar with Swage. And hopefully if you've joined today, you're at least aware of what Swage is. and we're going to learn about it in this session. So if we look here, this will be a video that's going to pop up on the screen. This is a short clip showing a Swage installation of the accessory on bus pipe. This is your standard seamless drawn bus pipe for substations. You have a glimpse of the press unit. You have the head assembly, and you see these teeth on the interior surface. That is the Swage die. That's where all the power in this technology comes from, is that those teeth and the way it's cut and the profile of the head assembly that it is mounted in allows for that die to grip all the way around and apply that interior pressure full 360 degrees. So unlike the old hex dies where it just sandwiches together, the dies flex and morph and you get that pressure from all directions. So we'll watch a short little clip showing what the Swage video looks like. You can see this is a 2-inch seamless pipe with the accessory. You can see the slight gap sliding over the part. A few seconds later, you see full die closure, and that gap on the middle surface is now completely gone. What this is doing is it's plastically deforming the bus as well as the accessory to build that crimped, locked-in connection right there on that interface layer. This specific one, you can see a little bit of that line just due to the section being cut in half, and you are going to see some axial growth when you're crimping in this orientation. So it looks a little bit different than what you would see in the field, which if you cut one in half, you'd be hard pressed to find that seam line between the aluminum bus and the aluminum connector that we ship for it. This here is the exact same picture from the video we saw before. That is your Swage press with the head assembly and the dies. This is what the fitting will look like after installation. You'll notice there's the teeth mark around here on each end. Those teeth are self-shielded, so there's enough compression in here and enough of a dip down to actually shield this at upwards of 500 kV for standard bus pipe runs. So this can be run at high voltage solutions without dedicated corona rings to protect those sharp edges because they are recessed down in that part. When you compare this type of permanent installation of Swage onto a bus pipe, it'd be kind of akin to welding, which is where the weld is applied and you are not going to just unbolt this and move it down the run. You have physically deformed the bus. It is a permanent connection, not meant to be removed. If you do need to remove it for any circumstances, we can obviously provide longer versions of this pipe to kind of make up that added cut length. But the benefit here is you guys saw the video, and those on this call have hopefully seen or are aware of the time it takes to weld up a fitting in a substation environment. The Swage, just with prepping, cleaning, and running that tool, you're looking at 3 to 5 times faster. So instead of 20 minutes, you're sub 5. And all that time really adds up when you're talking about a few hundred of these fittings on a substation. The beauty of Swage, you saw that press assembly where it kind of bottoms out and the dies flex in. We also provide a go, no-go gauge that allows you to evaluate that the crimp you just did reached full pressure. That means if it gauges around there, we know your connection is good. There's no more checking. If it gauged okay, you're squared away. Whereas welding or any of the other styles of technologies, sometimes the inspections after the fact are just as tedious as installing the part itself. So with Swage, we not only make it easy, we make it repeatable with that go, no-go gauge. On top of that, because this is a fully enclosed hydraulic system, as long as you're keeping those die teeth clear of debris such as gravel or rocks or lots of mud, you can install Swage fittings at any weather condition, be it snow, in the trenches that are still covered with water. In theory, you could run this tool fully submerged if you have a grounding grid that it rained overnight the night before. You can get down in there and you can crimp those fittings without having to have any more of those weather delays. Again, just really want to hammer home this 360-degree aspect. Because the die flexes internal to that shape, it allows us to get inward pressure from all angles on the circumference of the fitting. Because we strongly believe that the tooling itself should not be part of the detractor for these fittings, a lot of Swage companies will provide their tooling as a rental style agreement. So if fittings are purchased, you don't need to acquire the tools yourself. That can be rented out in those environments. But the pump comes with it. As long as you're getting 10K hydraulic fluid pressure out of that, it doesn't matter where it comes from. If you have a battery powered pump, if you want to use the accumulators on the bucket trucks, as long as you are reaching that pressure, you will get a full die bite. And you can validate that with the go, no-go gauge that is provided with the tools themselves to validate that that was crimped all the way down. Hopefully, the first question you have with that is, well, hey, Dan, what happens if it didn't crimp all the way? Let's say that gauge, it doesn't go over the go side, meaning we didn't have enough physical compression. You may need to check out the tool, reconnect it, make sure your hose is tight, double check the pressure output of your pump. You can run it again in the exact same position. There is no detriment to the part or the fitting. You crimp it a second or third or fourth time as needed to ensure you hit that crimp closure amount. You should not need to do more than one crimp unless there's some other problem happening. So if it doesn't close all the way or doesn't gauge, most likely you're going to be reaching out for next steps for advice on what to do. One important thing about Swage is we can't come in and develop a new technology and say, if you ask for something, we'll develop it and get it to you in a few months. It's important to know that all of these products and all the typical connectors you see for your substations, we have in existence. They are out there, they are in the field, they are installed, getting cycles and amps on them right now in a variety of 230 kV and lower, as well as up to 500 kV applications. All of these fittings are out in the field, be it T-taps, angles for your A-frames, any angular version of a terminal, be it a 45-degree angle on the end, or even a 90-degree. Any angle you want, because we all know when you have an old substation you're trying to tap in, it may not line up perfectly. You may have an offset between one bus run and another that's supposed to be in line. Let's say somebody forgot to account for a foot of concrete. Your altitude is now 12 inches different from left to right side. Different fittings or custom ones can obviously be developed when it's needed. If you needed an offset coupler to join those two pieces of run together, you now have a rigid piece of bus that kind of looks like a little dog leg shape from that offset height. So all those features, if you can think it up or you can dream it, more often than not, we can create a Swage fitting for that custom solution. Everyone on this call for Substation knows there are unique parts for every single one. It's not as simple as a transmission line where you just need a dead end and a suspension unit. You need to have T's, elbows, grounding stirrups, bus supports, expansion supports, end caps. That entire family has to be out there. I should point out 6-inch is the largest bus size that Swage is intended for. The reason being, if you look at that 6-inch bus pipe, the physical tube that our accessory is made from is just shy of 8 inches in diameter. If you start going to larger bus sizes beyond 6-inch SPS, either Schedule 40 or Schedule 80, you're going to run into envelope concerns with the tool, which is why the Swage technology stops at 6-inch installations. Extending from rigid bus, we also have all your cable couplers, terminals, and fittings. Exact same family as before. This one is just designed for cable. This can be for your AAC, your ACSR lines. You'll note all of this is specified around low temp or your standard temp operating conductors. We do have on the side, please don't write it down too much, but I do know we're being recorded. There is some development work in place around Swage for ACSS. That high temp operation of the cable comes with its own nuances that need to be designed through. We're still working through what that means. It is very likely that these fittings will get beefed up. There may be double, triple, or even quadruple crimps to ensure we can handle that thermal stress through the entire lifespan of that accessory. And just looking between the two pages, I'll bounce back between them. This large one is a 65-ton unit for bus pipe. This smaller one right here I'm highlighting, that's a 45-ton unit for cable. You'll note they look extremely similar. Shockingly, one is just bigger than the other. But they both behave very similarly. The press pushes the piston, which sandwiches the jaw into the head assembly, flexing that die in all degrees. Now, one of the fun things recently is the grounding grid. A lot of the fittings in the past, a lot of users use CAD weld or exothermic fittings. That has its own risks and its own procedures associated. Some people will do some of the old style C crimps or indent crimping of an extruded copper die. You also have your bolted mechanical grounding fittings. All those are out there, but Swage is newer to the market as it relates to below grade installations. This here is an installation shown on copper, where you can see it crimp down over it. Again, it's only one crimp and it has the gauges as well. This allows you to speed that up, do a grounding crimp in a matter of minutes, as opposed to the other prep, and you can move on to the next line. We had an associate here that went out to the field with a second crew. 2 crews went out, they installed 400 grounding accessories within half a day. 2 crews running the tools, they ran through and they just crimped everything and moved forward. I think the biggest complaint we got back was the operators on site didn't get any overtime for the day. The copper-clad the grounding units themselves can be used not only on pure copper, but also copper-clad steel, if you are looking to use the more theft-resistant or theft-deterrent options for your copper grounding wires. Oh, did I see something in chat? Oh, okay. So just looking at, we had a EPC firm provide us a generic version of a substation grid, because sometimes this gets overlooked. When we're talking about substations, you see the fence, you see the lines coming in, you see the big pieces of bus pipe up in the air, but all of this stuff that's underground, people lose sight of. This is a very large grounding mat. All the lines that are cross-hatched across here are either pure copper or copper-clad steel to ensure there's no ground fault issues for anybody on site in the substation. You'll note a couple of these other dots or connectors. Those are taps up or down, be it into a ground rod that connects your system to the ground or up to a tower, which connects to whatever fitting or accessory you are trying to bond out within the fence. But if you look at a normal substation, a relatively small size one, you could be looking at 400 to 500 connectors very rapidly. So ensuring that you can install those quickly and repeatably without having to worry about weather, that's a big plus mark when it comes to that installation speed. Highlighting that weather and the working conditions themselves, seeing an example of some of these ground grids, that's not a very wide trench. If you're the guy that has to crawl down in there and hand crimp some fittings on cable or work with an exothermic mold or any type of bolted wrenches down in these trenches, you want something that's going to be done quickly so you can get back out of there. It also can kind of pool up water. If you've had rain previously or it's been a wet season, you still want to be able to get in here and do your crimps. With Swage, you can. In the Swage grounding product line, you'll note there's a lot of different versions of the fittings. You have fence post connectors that allow you to bond out the poles that go around your fence, around the substation. We've got smaller versions that can bond to the gates that swing open and shut with a flexible braid to connect them. You've got your grounding lugs with 1-hole or 2-hole patterns to attach to your structure or other systems you're looking to ground out. And then you have all the various configurations within the grounding mat itself, whether you need elbows, crosses, T's, offset versions, etc. There's a lot of different ways to design a grid, and there's even more ways to hook it together. So you look at this and you might be thinking, that's a lot of different parts. I don't want to have to buy that many. Or I want to be able to stock 1 or 2 of these. Depending on the cable size for what you're using, you could stock something as similar as this guy that I'm highlighting right now. That's a parallel connector. If you have 4/0 cable or 250 wire, you can pretty easily bend that in the field. So you can use this not only as a coupler, you can use it as an elbow, you can use it as a T-tap. This fitting becomes pretty modular to take the place of a lot of these other connectors. That way you can simplify your SKU list for what you're trying to inventory and just stock something you know can be used for multiple different arrangements. Everybody loves to see fielded pictures of these things. This is a ground rod in the top left that has been compressed onto a Swage grounding fitting, which is made from pure copper. The one just below it, you'll actually see copper-clad steel that's been stranded. The reason we know that, you can see the nice little copper layer in between. That's the outer layer on the copper-clad steel being smashed all together inside this fitting. The right 2 and the ones on the bottom ones are aluminum, but the 2 on the right, that is copper wire on a copper fitting. It looks like a solid cross-section. And that's the point I want to draw to here is the compression ratio for this copper is much higher than some of the aluminum fittings, which allow us to get that solid crimp, get that permanent connector between the cable, the ground rod, and the fitting itself. Now, before getting into more and more data, IEEE 837 is the governing standard for substation grounding. That defines the testing requirements. It defines what fittings you can or cannot use. Any requirements for grounding out a substation are developed and established in IEEE 837. I say that to preface this, there are 4 main types of grounding connectors in the market today. You have your standard bolted or mechanical. This has arguably been the gold standard for well over 100 years. Something simple, something conductive, and it bolts tight. That's its objective. The compression designs or your indent or your C crimps, very similar compression technology to Swage, albeit slightly less robust. just due to the die technology itself. Then on the bottom, you have exothermic, which is going to be your copper shot of thermite, which creates molten metal that fuses everything all together. And then on the right, we have Swage. If you look at the longevity, bolted mechanical have been out there for 100 plus years. Same with compression. Exothermic is up there. Swage is roughly around 20 to 30 years at this point. So a lot of history. Many users are still gravitating to the three outside of Swage. And what I'm hopeful to convince you of today is that with the latest IEEE 837 standards, if you followed through with that in 2014, they did a massive update to the requirements in that the EMF, or the fault current portion of the test, increased to much higher KA loads. Unfortunately, that meant some of your traditional or grandfathered technologies are no longer compliant with 837. I'm not going to come in and try to say I know every single test report for every one of these families, but I do know for certainty that exothermic will pass this new standard with the higher fault load, and I do know for certain that Swage grounding fittings can also pass this updated standard. This has all gone through the extensive sequential testing that 837 requires. All test data is available upon request. But if you're looking to keep up with the latest and greatest standards, what the industry is doing, the KA rating here will guide you to those more robust Swage-like designs for your grounding grid. Specific here to the Swage grounding side of it, instead of talking about all four of them, we'll kind of compare against the two common ones today, which are Swage and exothermic as they relate to copper grounding grids. Very similar to the bus pipe and cable portions. Certifications, they're not required for Swage. Once you've gone through the demonstrations, you've seen how the tools work, with that little handheld gauge that you can check the accessories afterwards, you know if that fitting was installed properly or not. You don't need to go through extensive inspections or any other follow-up. You gauge it. If it gauges good, you move on to the next one. With that, all that stuff can be used in any weather environment you want. It can be wet, it can be cold, it can be hot, it can be snow. That does not matter for the Swage equipment, whereas other technologies you may have to fight the crews to get out on a rainy day, or you may have to put up tents and evaporators and fans to dry out the environment to do those installations with other technology. A lot on here. Really just want to highlight Swage is meant to be simple. It is meant to be a fast alternative to welding. It's meant to be a permanent installation, something that will always be out there and meets all the standards that are required, either your NEMA CC1, occasionally some of the C119 requirements from ANSI, as well as the IEEE ones, the grounding ones, 837, IEEE 80. All of that we've taken into consideration for this Swage technology, not only for the above grade bus and cable, but also the below grade copper. It is versatile for both of those connector types. So be it aluminum, be it copper, above grade, below grade, all of that Swage technology we highly encourage and recommend. If you'd like to learn more about some of that Swage technology, we have a series of white papers on our AFL Global website. This link in the presentation today takes you to a specific one, detailed white paper about some of the testing and more advanced data that I haven't talked about today. But if you're curious, feel free to click on the link, check out the white paper, and reach out for questions. And with that, that's my little blurb on Swage and substations. with a little bit of focus on swage grounding. So thank you for your time, and I'll take questions now.
Okay, thanks very much, Dan. Good presentation. A lot of detail in there. We do have a couple of questions here.
Yeah.
Um, how does the 360-degree swage compression improve reliability compared to exothermic? How does it do that?
So the 360 degrees itself, um, by itself, may not be explicitly an improvement. Both of them can create a permanent connection.
Hmm.
What we're striving for is that repeatable and gaugeable or inspectable after your crimp. If you look at exothermic, what is the inspection method to see if an exothermic fitting was good or not? Does anybody know off the top of their
Okay.
head?
Oh, I don't know.
It's a hammer test
Oh, that's right.
where they hit it with a hammer, A, to knock the slag off from the exothermic reaction, but to see if the cables fly apart. Our swage technology, it's not a hammer, it's a gauge. We
Hmm.
know what that go size is, the no go size is. If it crimps down enough, we know we have that compression. And that's where your reliability improvements are going to come from.
Okay. Here's another one. How does swage perform in poor or corrosive soil conditions?
It performs the exact same as your standard copper alloys.
All right.
If you look at the old mechanical styles, those are silicon bronze or brass alloys.
Mhm.
Swage grounding is made from pure copper, so it's going to perform the exact same as your copper wires or any pure copper fitting in the dirt.
Okay. Which IEEE which IEEE 837 test is the most challenging?
My personal opinion is the EMF fault test. At the very end of the sequential evaluation, that's where it's gone through all the freeze thaws while submerged. It has gone through an acid bath to eat away 20% of the conductor, and then it still has to survive an EMF fault current afterwards.
Okay. What are the main failure points of exothermic connections that Swage eliminates?
I think part of that is just the variability in how the connection is made.
Okay.
Exothermic is a very
Yeah.
violent and chemical reaction, whereas swage is a strictly mechanical one that you can watch it close down and you can gauge it to ensure you have that reliability.
Okay. Do you know how does copper coated steel compare to copper solid copper during fault current events?
Interestingly, they are very similar. If you look at IEEE 80, there is a chunk of equations. I affectionately refer to it as the T-cap equation, only because that is one of the variables in it. But in that, it breaks down the variables and material properties for both pure copper and copper-clad steel. Copper-clad steel does need to be upsized slightly from pure copper if you want to maintain the same fault rating.
Okay, I understand. Right. Okay. Okay, excellent answers. Good questions. Thank you very much for those. And good presentation. Thank you again to AFL for participating with us. Appreciate it. Okay,
Absolutely. Thank you
thanks.
all for your time, and thank you, Randy.
Thank you. All right, thanks. Next up is Critter Guard, John Sims. Um, where are you?
Trying to get that to work.
Okay, if you would share your screen, I'll make your introduction. All right.
Okay.
Okay, the next presentation in our live online forum today is from Critter Guard. We have with us John Sims, the president of the company. He's going to be talking about squirrels are more dangerous than cyber hackers. I love that title. Okay, and he'll explain why he thinks so. Okay, here is John Sims. He's, as I mentioned, he's president of Critter Guard. John has more than 40 years of experience in engineering, product development, and sales management in industrial utility markets. He's a veteran of energy storage systems, i.e. batteries, process controls, and material science. He has hands-on experience in more than 50 countries worldwide. And he has gained a Bachelor of Science degree in chemical engineering from the University of Missouri, Columbia. And anyway, so if I would get you, I see you started your screen. That's great. I'll hand out his presentation. And if you have any questions for John, put them in the chat and we'll relay them to him after the presentation. Go ahead, John.
Very good. Thanks, Randy. Just to double check here, make sure you can hear me.
Yeah, everything's fine.
Okay, great. So, appreciate the introduction. Thank you, Randy, and thank you everyone that's joining remotely here. Um, yeah, Critter Guards, we've been around, 25 years now. We're a small business, headquartered in Kansas. We've been, pretty much one claim to fame, and that is keeping squirrels from causing animal outages. So the presentation is a little humorous look at what people have said about, squirrels. They're, fun to talk about. Everybody sort of gets a snicker when you say, well, what do you do? Well, we keep squirrels off power lines. Um, so it's like, really? Is that serious? So we'll talk a little bit about how serious that is and what some of our customers around the world are saying, as well as some third parties. So just to start off with some kind of older quotes, but these are still relevant today. Gentleman Marcus Sachs was Senior Vice President, Chief Security Officer at NERC, and he said about 10 years ago that cyber hackers was what everybody was worried about. The Russians, the Chinese, whoever, that, nefarious actors would hack into the grid. But he made it clear that squirrels are still the number one threat to the grid. Uh, Similarly, John Inglis, former National Security Agency, basically admits that the number one threat experienced to date by the U.S. electrical grid is squirrels. And any of us that have ever seen a substation blow sky high to come back later and find this roasted squirrel, we know that's true. So it doesn't really seem to matter. This chart is, again, somewhat dated, but recent data indicates that it's still accurate even in today's time frame. There's no shortage of squirrels, and as Randy mentioned, I've been around the globe in various walks of life. There are squirrels in every country, or squirrel. They may not call them squirrels, but they're small crawling rodents, and they cause these kinds of problems. So you can kind of see there is a seasonality in late spring, early summer, and again this time of year. It comes and goes, but the threat is always there. To bring it a little more current day, Critter Guard has now for several years maintained our own outage tracker. So basically, we go out and web crawl the internet when there's a public statement by the local news in Timbuktu. It makes the papers. We had an outage. Our web crawler will find those and we track those over the course of a year. And then we update that, on a periodic basis. So if you're curious, take a look at that link, critterguard.org, for the power outage stats. You can just do a search if you want to in our search engine and find that. Some other recent data in 2023, we know that there's a lot of events here. I mean, there's over 5 million customers that have lost power, 74,000 individual events. It's expensive to lose power, regardless of what sort of business you're in, small, medium, or large. Some of those outages can really cost serious money. Um, just animal related only in 2023, over 7,000 outages caused by squirrels. We get a lot of this data from American Public Power. There are polls and queries, going on all the time, and we constantly pay attention to those kinds of things. So it's a very prevalent thing. So you could say, well, gee, Critter Guard must not be doing a great job because there's still all these occurrences. We're not killing squirrels. We've got customers that say, hey, how do I do this? And we talk to them about Critter Guard, and they say, oh, well, we just use a shotgun for that. Well, you can probably do that depending on where you're based. But the governments tend to, and your neighbors might frown kind of strongly at that remediation technique. More stats here in 2020. Utility customers specifically said over 1.3 billion hours of power outage. 2019, 1 in 4 companies says that happens at least once a month. And squirrels, I can't remember who made this comment. This might have been American Public Power, definitely. And that data has been consistent year in and year out, depending on where you are, at least in North America. The Northeast and the Midwest are the two most prevalent regions for squirrel-caused outages, and happens every year. And in just specifically from Entergy, one of our large customers, they said in 2019 they had more than 15,000 animal-related outages. So it's not a trivial problem. Happens a lot. Costs of animal outages are very expensive. We've got estimates ranging up to 10 billion, over the entire industry. Animal caused outages can be over $1 million per episode. We had one close to us here years ago in a substation, small municipal utility that had, uh, you know, traditional animal mitigation covers and guards. Squirrel bypassed all of that, and literally it looked like a firework display. It was an unbelievable thing that made the rounds on Facebook and social media. So it's definitely a serious issue. So, and again, especially with some of the new technologies coming, drivers I'm talking about here, if we look at some of the efforts that utilities are specifically saying, we're going to put more effort toward this to solve this problem. Some of you, depending on where you're working, you may have programs like this with similar names. These are just some I came up with. But, well, we're going to focus on substation reliability. We're going to focus on grid hardening. One of our customers calls their program Perfect Power. Everybody's got a name for how we're going to take care of it. Our question is, don't bypass the obvious. Is animal mitigation part of your strategy? Because you can do all these high-tech things, but if you're bypassing or ignoring the simple strategy of animal mitigation, you're missing out on a big opportunity to solve some problems at a very low cost. So the rest of this presentation is going to focus on, okay, well, what's CritterGuard all about? Why are we here? What's different? And so we'll go through kind of what we do there. That starts with just getting the context of what we do. It's called Critter Guard, so we're keeping critters at bay, but there are lots and lots of guards out there by multiple competitors. Most of them take a form similar that you'll see on the screen here. They're covers or guards or even shields or blankets, any number of different, and they're all for different sizes and different voltage ratings and different configurations and spacing. Many of them are specifically molded out of advanced or other high-tech materials for insulation resistance and dielectric strength, and on and on and on. CritterGuard doesn't take that approach. We're very unique compared to most of those other suppliers. Those guards for the competitors are designed to fit over a device, a terminal, a bushing, an insulator, any number of other terminations that are live and energized. So the guard has to specifically be designed and fit for that specific device. Line guard and pole guard from critter guard don't take that approach. How can we do that? And the answer is we block the access rather than cover the device. So it goes back to how do we come up with that thought years ago? And the question is, what is common among all overhead equipment? Well, they're all connected to something. They all have a conductor of some size and some voltage rating connecting that device. Most of the utility industry is not worried about the conductor itself. We're interested in the termination point where that bridging effect could happen. A squirrel with four legs crosses or bridges two live phases, and boom, you've got a problem. So the animals use that conductor not as an end in itself, but as a highway. They're just trying to get someplace. They're curious, or they hear some buzzing, or it's warm, or their buddies said, hey, the party's down here, or whatever. So, line guard for overhead power lines, and actually, it doesn't just have to be power lines. We have a lot of telecommunication customers, cable TV, telephone, you name it. If it's an overhead line and it can serve as a highway to a squirrel or any other rodent, a snake, any number of things, line guard blocks that highway. So it's independent of what those devices and what those voltage ratings are. Similar to that, our pole guard blocks access from the ground. So an animal that tries to crawl from the ground up to a pole-mounted transformer can't get there because the highway, the pole, is blocked. So we have the mechanism of basically creating a virtual overhead fence. So line guard is actually a universal solution for overhead protection. It's the name says line guard, but in fact, we're not actually guarding the line, we're guarding the assets on the line. And instead of just guarding it, it's actually repelling them. It doesn't do anything until it's acted upon by the animal. It just sits there. So there's absolutely zero effect to electrical properties. It's not affecting voltage, it's not affecting insulation, it's not affecting, any of all the line spacings that you would have anyway still apply. So it's simply a dumb plastic device sitting on the line that in fact spins or moves if and when an animal comes upon it. And he'll do that because he's curious. What we've found more often than not with animal behavior, as soon as you put something on the line, they come check it out. They're curious. So they're not necessarily intending to be nefarious. They just want to come see what's there. And so our design basically moves or spins around the conductor once the animal engages with it. And that makes him unstable. It turns him upside down. He's got to hang on for dear life. And so that's a problem. So, and then we've learned over time, this actually works with pretty much anything that crawls. As small as a mouse, larger issues like rats, monkeys, sloths in many overseas and even domestic environmental refugee, what's the right word, parks that have protected species. A sloth is a good example of that, but other animals as well. They will use the overhead lines to escape predators or just to feel more safe because they can crawl on the line and the fox or the dog or the wolf or whatever can't do that. And so they will escape to higher terrain and the conductors give them a chance to do that. So that's why they're going up there. And I'll also add that's also why we see a lot of this with distribution power lines, somewhat transmission, but the higher that you go in elevation from ground level, the less of an issue animal mitigation is. With the exception of birds, um, the crawling animals don't usually go much higher than the first line of defense, which are those distribution lines. So I'm going to switch here, Randy, and go to a video. Make sure I get this done correctly.
Okay, let's see if it
Um,
works.
there we go. We'll share that one. And that means I've got to go to this one. Hopefully we can see that. Can you see that?
Yeah, it's fine. Oh,
That's the
there it is.
video plan?
There it
Okay.
is.
Okay, so this is squirrels are not good trained actors. It's very difficult without a lot of patience, more than I possess, to get a squirrel or any other animal to actually do what you want him to do on the line. So in this case, this is a homeowner customer who installed this on their overhead service entrance line, and was lucky enough to get this video. Now he called it a squirrel, but we think it's probably more of a rat. You can see that tail is not a
Yeah.
bushy tail like a squirrel, but same difference. And what the squirrel has done, he's come from the right-hand lower corner of the video. You see he's given up on it. He checked it out. He turned him upside down. He hung by his feet. He finally gave up and went back. Now he's come back again, trying one more time, turns him upside down, finally gets frustrated. And about this point, he's going to say, there's got to be something else I can do. This is why we call this a jump barrier wheel, because it makes him jump over it. Hang on just a second. It makes him jump over that, and then what happens is it spins him off. Okay, now we're back to the presentation. Do I need to share that again, or can everybody see that?
We see your presentation. It's fine.
Okay. All right, so the question is, well, where can I use that? And the answer is pretty much everywhere. If it's an overhead conductor, um, we already mentioned that video you saw is a single phase line, but we have these on lots and lots of three phase ground lines, neutrals, doesn't matter because it doesn't affect anything to do with the electricity supply. So it's just basically a spinner on the line. And so what we tell customers to do, you can put it anywhere on the line between where you think the animals come on the line and whatever you're trying to protect. Maybe a transformer, maybe a substation, maybe a switch, a recloser, any number of things. Whatever's on the end of the line that you want to protect, instead of having to cover that device, you put a blockade on the highway so the animals can't even get to that device. So you can put these up in one of two situations, either de-energized. We have some lucky utilities that have enough redundancy they're able to, put these on de-energized. But we also have what we call hotline clamps. These are easy to install. The line guard literally snaps over the line, so you can wear your insulated gloves. And then we have large solid aluminum block, C clamps, if you will, that can be, with a wrench or a eye bolt hot stick. You just screw it down tight on whatever conductor you're putting it on, and so that keeps you from having to shut down the power. Um, we have a standard size. The rollers are designed at 1 inch openings. Most conductors are less than that in diameter, but the critical requirement is that the roller be able to spin freely on the line. And there's a series of rollers. There's 5 of these, and they're all independent. So you don't want to get by with 2 or 3. A squirrel will jump those. So you want all 5, all spinning independently. But if your conductor And a good example of this would be like either a triplex type line with sort of a twisted rope is what we call it, where you've got maybe two conductors or even three, and then a reinforcement cable. Those conductor bundles, if you will, can be quite large. Anything over an inch, you have to cut the rollers back. We used to have our customers do that. You can do it yourself, but we started offering it because it was so popular. And we started off in that as well. So we have what we call a triplex kit, which is the same kit. It just has larger openings on the rollers. And then we've got applications again from single phase up to the largest I know of, even though it's larger than what we spec. We know we've got customers using these on 77 kV lines. There may be some higher than that, but we don't know where every customer is using it. This gives you the example of we talked about the T stands for triplex. So if you have a cable bundle that's multiple conductors and a reinforcement cable, then that roller opening has been cut back to be larger so that the roller can still spin it. If it doesn't spin, it's a useless system. It will not help you. So it has to spin. And then we've got these clamps that we had special made. Important because the edge of the clamp, the face of it, has to be smooth because we want that face of the roller to be able to spin freely against it and not get hung up when a squirrel or a rat, as you saw in the video, engages with it. So that's line guard. The second way that we deter these pests is with pole guard. Pole guard, same principle applies. We treat the pole like a highway for critters to get to the overhead assets. Pole guard blocks that. So we use rigid plates. They're fixed around the pole. They have 7 rollers around the plates. And so it's a literal blockade. The animal has to hang upside down on the plates. They've got little holes in it so he can see through it and it tempts him to want to keep going, but there's no way over it except around the outside. And when he tries to get around the outside, he's going to grab hold of a roller that's going to spin and he can't get his claws in it and he's done. So other types of wraps that are very ubiquitous, no disrespect, but we've seen animals just jump right past them. You give a squirrel a head start and boom, he's right over it. So pole guard, they can't get by. So we're going to go back and find another share here. This started on me accidentally, but again, squirrels are not trained actors. Can you see that again, Randy, this new video?
Sorry, John, I have my mic turned off. Yes, I can see it just fine.
Okay, so squirrels are not trained actors, so I had to get this one from a pecan tree. We put about the same diameter as a power pole, in this case, a wooden power pole. You can see the pole guard mounted around the pole, or in this case, the tree. The squirrel is doing his darndest to try to get by it, works all the way around it, keeps trying, and sooner or later he's going to give up because he just can't figure out how to get over there. This particular video, I don't think I got an example of him trying, but if they grab that roller, it spins and they can't hang on to it. So that pole guard plates, the same design, we use it for steel, concrete, and wood. And so it doesn't really matter what the pole is made of, but it must be round. It is possible. We've got minor examples of sort of rectangular poles or other geometries. So it is possible, but that's definitely a custom item. So just some examples here. This is both pole guard for a wood pole as well as line guard, but applied in a slightly non-traditional sense. In this case, guy wires that are not horizontal. They're on obviously the angle, and yet this customer, this is a water treatment plant. This customer put these up because their installed guy guards that are fairly ubiquitous weren't doing the job. So they added our line guard over and above their traditional guy guards, and problem solved. Completely, problem disappeared. So you can see on the wood pole. So basically, this picture doesn't show what's at the top of the pole, but that's clearly what they're trying to protect. Another couple of interesting examples. Picture on the left shows a steel pole. And so exact same system, it just mounts differently. And so it uses the same sort of steel tensioning bands that we have for street signs and things of that nature. So it's actually easier to install than the wood pole version. And we're hopefully to move to a more standard system, irrespective of the pole, but that's where we're at right now. And then you can see on the right, if there's a conduit up the pole, these get very specific. The spacing has to be sort of just right, but that's a nice, 4-inch conduit that's also stepped off the pole. And we were able to come up with a mechanism to extend the pole guard in sort of an oblong direction, and that still worked. So that can be done as well, but obviously those take a little more discussion back and forth. Pole guard can be used on just about any round pole. The ideal mounting location is because most distribution power poles will rise as they get taller. And so the diameter shrinks a little bit. So if you can find the point or the height where the diameter is roughly 12 inches, that's how the plates are molded, is for a 12-inch diameter. 305 millimeters for those of you in the SI system. And for smaller poles, if there's too big of a gap, let's say it's a 9-inch pole or a 9.5 or 10 where you're going to mount it, and you've got maybe an inch or inch and a half gap between the pole and the plates, we have this very simple flexible conduit that's easy to install. It just sits above the system, and it can actually be zip tied to the pole guard plates so it doesn't, squirt away. But that's a flexible wrap that will block that gap between the pole and the pole guard plate system. And again, as I said, we can mount it to steel, concrete, wood, um, and custom designs where appropriate. Okay, so if we take care of most of the crawling animals that are going to get up on the line and stop that, what does critter guard have for birds? Well, it's been a challenge because we've learned that birds don't behave like animals. What's great about crawling animals, from our perspective, is that regardless of what type of animal you're talking about, the behavior on a power line is very similar. So whether it's a squirrel or a snake, the reason they're there, how they act, is pretty typical. Unfortunately, with birds, they're not like that. So if you've got a problem with birds of prey, hawks, eagles, ospreys, large birds, they tend to be hunters, and they tend to, for the most part, tend to be loners. They don't like competition in their hunting ground. On the other hand, small birds like sparrows, wrens, pigeons, swallows, you name it, those birds fly in flocks and groups and have this sort of, um, you know, uh, group mentality. So we came up with this technology. It's kind of our version of it. Um, it's not a mechanical diverter. It doesn't scare anything away. The birds just don't like it. It's a scent that's based on a technology that's well known for birds. But what we did was we made it long lasting. this is a chemical that's safe and environmentally friendly. But the downside of it was you'd use it in a fogger, for instance, and the next day you couldn't tell you ever used it. Well, that's not all that great. And so we developed this formula that will last up to 4 months, have a couple of different formulations of it. So when you hang it up, and that's what you do, you literally just hang it, and it creates a scent that the birds don't like. And they will literally leave the area because they don't like that smell. It gives them a headache or who knows what. So they just move on, and that's all we care about. We're not trying to kill them. We're not trying to cage them. We're not trying to relocate them other than by their own volition to say, go someplace where it doesn't stink. And so this has worked well for us with a variety of substations where you have sensitive equipment down below, might be a control cabinet, transformer cabinet, it could be phase bushings, any number of things where birds will roost or nest above on the structure, the substructure, and then poop all over down below. And everybody hates that. Nobody likes it. And since you don't really know where they're at, no one's at the substation, it's hard to tell. And so by putting up the bird block, you literally just hang it sort of all over with recommended spacing depending on the problem you're trying to solve. And we'll work with you on that for how much you need over how much of an area. But we find that most utilities will pick a small area that's sort of a target area. Again, it might be a bus bar, a control cabinet, or something that they're very concerned about. And so they just put some in a specific area and the birds are gone. They don't come back. So that's just a wonderful thing. We say it's a vapor barrier. What it is not is a force field. You can't just hang it up and expect that the birds won't approach it. Birds, like the other animals we talked about, they're curious. They're going to check it out. So they'll come and they might light. They might, perch someplace. But if they get a whiff of this stuff, then they're going to move on. And we've seen by customer testimony, we've seen uh, groups of birds, up to hundreds, that in about 2 days or three at the most from hanging up the first application, the birds are gone. They're down to one bird, and then a day or two later, zero birds. And so, and what we think happens, even though this does have a shelf life, it will fade. The scent is not as strong over time. But even when that's the case, the bags still hang there, and it's all organic, so they'll just rot and fall down at some point. But if they do, or before they do, the birds will recognize these little cotton pouches hanging there, and they know that that was the source of their uncomfortableness, so they don't come back. And again, that's one of the other objectives that we have from the line guard and the pole guard products. No maintenance. Once you put these up, you don't touch them again. You don't have to go back. You don't have to do anything. There's no, you don't have to take them down for thermography. You don't have to, do any of that. We've got bird block and substations, overhead lines, cross arms on poles, generator stations, warehouses, service garages. These are kind of fun. Um, the service guys absolutely hate birds all over their trucks when they're getting ready to load up for the day. And they're in high bay ceilings, the birds are flying in and out. They crap all over the stuff in the truck. And now you got to deal with that. So you hang it up in a warehouse, never have to deal with it again. So that's a nice thing. There's just some examples. Two different subs. The one on the left is a large nuclear power station. You can see the gas-filled phase conductors at the top, and they're literally using hot sticks to hang the bags. You can see a close-up of the bags at a different substation on the right, where a live substation didn't have to shut anything down, literally just hanging the bags looped together because we recommended a specific spacing and they didn't think they could get them quite that close. And so we doubled up the bags in one location to make a stronger scent in one location so it would propagate further. And that worked. So, and that particular substation you're looking at was right next to a nature preserve with waterfowl all through the area and had been for years. And once these bags went up, they left. They just got trained. It's like, we're not going to go back there. So that's kind of the story. Um, Basically preaching to the choir, I hope, but don't wait for your next animal outage. You know it's going to happen. It's just a matter of time. But consider Critter Guard because we're not like those other guys. We're distinctly different. We block the highway rather than covering a device. Doesn't matter what the devices are, it gives you pretty much asset protection all over your entire footprint. So, and again, once installed, no maintenance and no repeat outages. We were constantly amazed by that, um, you know, examples like Ameren and American Electric Power and Entergy and you name it keep coming back and then they keep buying more product. And it's like, are you replacing these? No, this is new. I said, well, what about the old ones? We never have to touch them. Once we put them up, we never go back. So we're proud of that. Look forward to your interest. Give us a call or a shout or get on the website, and we're happy to help you out. Appreciate your time and attention. And any questions, we'll go from there.
Okay, thank you very much, John, for the excellent presentation again. Thank you very much. We got a couple of questions. A couple of questions that have come in have been about weather related.
Ah,
So
okay.
the first one is, how do your products hold up under high wind loading or severe storm events?
Yeah, good question. Um, First of all, until the poles blow down, we haven't had that problem. And part of the reason is that, first of all, we've had the product designed in such a way, it has what we call weep holes. So it's designed, first of all, to let air blow through it. And as long as it's installed correctly on the line so that those rollers don't slide apart, the whole system needs to stay together. And so it doesn't need to be jammed together, so because each roller needs to spin independently. But as long as it spins independently and freely, the wind will not harm it. We actually rigged up a test some years ago with a third-party engineering firm and put a torqued angle on the rollers on a conductor line to specifically measure whether the spinning of the roller would actually wear onto the conductor or the conductor's insulation. Long story short, the wind would have to blow at that angle, at that speed, which was like 60 to 70 miles an hour, at a specified angle for more than 30 years straight, continuously, for there to be a mark on the conductor. So the answer is it doesn't do any damage to the conductor, even if it could spin that much. And it doesn't freeze because it's got these weep holes. So if it rains and then freezes, when it does thaw out, it'll run out of those weep holes and not freeze onto the line. But anecdotally, the right way to answer the question is the Canadian military uses it for years and years and years in their electrical systems. They get lots of snow, obviously. It's used throughout Central and South America, in Florida and the Gulf Coast and Arizona, where the sunshine and the sun is actually probably the worst enemy, even more so than wind and rain. But our unique formulation of UV and colorant has stood the test of time. We've used that combination now for more than 20 years and had third-party testing done on the UV cycling, and it doesn't crack or haze or any of that. So we've got a very long-lasting product that
Mhm.
will stand up to the most severe weather conditions anywhere in the world.
Okay. Next question related to weather was, how does the product perform in extreme climates, ice or high heat, heavy
Yeah,
rain?
so as I just mentioned, I mean,
Yeah.
certainly high heat is no, I think that right off the top of my head, I don't remember, but it's on the website, technical
Yeah.
data sheets. I believe the plastic will go up to like 160 degrees.
Yeah.
So if you were, in a high voltage, high current area where you're generating more than 200 degrees on the conductor, that might be questionable.
Mhm.
Whether
Yeah.
that would be recommended. Certainly, ambient temperature in direct sunlight, that's no problem. It's certainly stood its test of time in 120 degrees ambient conditions with no issues whatsoever. As far as cold and ice, I just talked about that. So, I mean, it's been New Hampshire, Vermont, Maine, uh, feet of snow. And certainly, obviously, snow will cover the lines, but once it melts off, it weeps out of these holes and it's as good as news. So the water just runs out of the system.
Okay, about bird block, how long does it last in harsh outdoor environments?
That's subjective. The harsher, the less it's going to last. All of the ingredients in the formulation, first of all, they're all organic. They're all food grade safe, but that also means they're water soluble. So if it's in a flood and monsoon season type stuff, it's not going to last very long. We actively recommend customers that are going to deploy take a look at your weather forecast, and if it says that you're going to have a period of extended rain, then wait a couple of weeks before you put it up. um, the but so yeah, in normal conditions, normal weather, I've literally seen a couple of sites that we cooperated with and put some up. Um, I went back 8 weeks later after the first installation. The smell was only supposed to last about 8 to 12 weeks. We didn't even get through the fence in the substation before both the lineman and myself went, "Yeah, I can smell it. It's still pretty strong."
Yeah.
And it had snowed there, it had
Hmm.
frozen, it had rained, normal rain, like 1 inch
Yeah.
rains and things like that, and you could still smell it. You could tell discoloration in the bags, but there was still an active smell and, no problem. Obviously, if it got in a flood zone or actually literally drenched, then I wouldn't recommend that. But
Okay.
that's the experiences we've had.
Voltage levels. What voltage levels or conductor types are best suited for the product?
For what product are we talking about?
For the line guard system. What
Yeah,
voltage
the
levels or conductor
from
types are
from a
best
test
suited for the
from a
line guard?
test data perspective,
Yeah.
we spent a lot of time some years ago. Now the tests have all fallen out of favor, but there was distribution testing. And that basically meant anything up to 38,000 volts.
Okay.
So from a technical testing perspective, ASME and IEEE testing for wildlife mitigation products, these have all been rated and tested over all the appropriate test vehicles up to 38,000. As I mentioned, we've got some customers that have deployed at much higher levels than that. I don't know anybody that's AEP talked to me one time about doing it at 384,000 volts. We haven't done that. I don't know that that's a valid concern. I mean, how many animals are going to be at that height and
Hmm.
that voltage?
Right.
So, but certainly at the distribution levels of voltages, no issues.
Okay. There was a one mention here about squirrels and rats, but what about snakes? Has
Yeah,
it been
snakes are
tested with
definitely one of the
snakes?
repelled species. In fact, I had to get trained by
Uh-huh.
Duke Energy, who told us that it's like, yeah, we actually use it quite a lot for snakes, especially in North Carolina, which was in the news quite a bit a couple of years ago with all the flooding. But when the floods come, the snakes come out and they crawl the poles
Hmm.
looking for food or shelter or safety. And we found out both pole guard and line guard are effective against snakes.
Okay.
So, been
Hmm.
very happy with that.
All right. Okay, so that's it for the questions. Again, lots of questions, John. There's
Well, I
always interest
appreciate
in
it.
in
Uh,
this.
The audience is always great to participate in these things, so thanks very
Yeah.
much.
Okay, great. Good presentation. Thank you very much again. Thank
My
you.
pleasure.
Okay. Next up, Alan Reinstra. Where are you, Alan?
Here I am.
There.
Here
Okay,
I am.
great. Thanks. If you would share your screen, I'd appreciate it.
Happy to.
Okay, the next presentation is from SDT Ultrasound. We have Alan Reinstra with us from the company. It's on ultrasound condition monitoring for substations and other high voltage electrical systems. Alan is he oversees SDT ultrasound solutions operations across 6 continents. With more than 35 years of experience, he has guided thousands of organizations in adopting better practices for condition monitoring and asset health management using his proven 10-step strategy: inspect, detect, measure, trend, analyze, act, and report. Okay, that's great. I see your screen there is ready, and so if you would take it away, I'd appreciate it.
Great. We're all set to go. Thank you so much for joining. Really always a pleasure to be on these events with Electricity Forum. Thanks a lot, guys. Today, I'm going to speak to an issue that's critical on so many levels, and that is electrical asset reliability and safety. And I put reliability and safety in the same sentence because if you don't have reliability, you cannot have safety. A reliable plant is always a safe plant. Unreliable electric power systems not only cost millions of dollars in downtime and repairs, but they've also got the potential to maim and to kill. So reliability leadership really needs to step up here. They need to focus on the preservation of both physical and human assets. Everybody that comes to work has the right to a safe work environment, and they have a right to return home unharmed. So what this presentation really looks at is the problem, which is an unreliable, aging infrastructure, and specifically around electrical assets, whether it be substations, transmission, distribution lines. We all know, we see it in the news, we hear it every day, that the infrastructure is aging and it's not able to keep up with the demand. What I'm going to present is a solution, the technologies that can give us an early detection. Early detection is everything. We need to know when problems are about to occur so that we can get on it, schedule repairs, order parts, and know before an outage event shuts us down. At SCT, we have a simple mission. We wake up every day with one thing in mind, and that's to enable our customers to achieve their operational objectives by advancing the reliability of their assets. And we do that by providing leading edge technologies built around ultrasound, the ability to detect ultrasound, high frequency sound, convert it into audible sound so that we can hear and know when our assets are changing in their operational condition. Today, two topics to cover. One, what is ultrasound? And two, electrical maintenance. We'll start with what is ultrasound. And in this, we're going to talk about sound characteristics, friction impacting and turbulence, and the 8 application pillars. So really what this is just let's call it an ultrasound 101, just a real 30,000 foot level on what is ultrasound and how can it help make my life better in context of reliable electric assets. And then once we've covered that little briefing, we're going to jump into electrical maintenance. And with electrical maintenance, we're going to talk about these topics: the importance of electrical maintenance. I'm going to take a quick look at NFPA 70B and NFPA 70E, 2 standards by the National Fire Protection Agency, so we can have a look at what each of those standards, what their purpose is, what they mean to us, and how they can help us find common failure modes. Then we're going to look at a couple of case studies, and we'll finish things by looking at specific ultrasound technologies that we manufacture and provide globally for our customers to maintain their electrical assets. So let's just jump in to what is ultrasound. And I always like to start this segment by talking about what is ultrasound in terms of the 3 different, sorry, I gotta I got to adjust my screen here because I can't see one thing. There we go. Sorry about that. So in terms of sound characteristics, what we want to look at is the three different classifications of sound. The first one being infrasound. Infrasound is low frequency, below the human range of hearing. Certainly good for seismic sensors to detect earthquakes and tsunamis and things like that. Underground detonations, but not really much good for humans because we can't hear them. Audible sound, so in that 16, that's not right, 16 to 20 kilohertz, no, it's basically up to 20 kilohertz and just a few hertz. So I think it's supposed to be 16 hertz to 20,000 hertz is the range or the scientific definition of human hearing. I can attest on my latest hearing test that I can only hear to about 11 or 12 kilohertz, but that's partly due to injuries in my youth and being exposed to high noises through my working career and just the fact that I'm turning into an old guy. So what we tend to lose as we get older is our higher range, our higher frequency ranges. And the good news for us is that the human sounds, our voices, and most of the sounds that we listen to are in that sweet spot of around 2 to 5 kilohertz. So I'm going to put off getting a hearing aid for a little bit longer yet. When we get above 20 kilohertz, we are now in the range of what we call ultrasound. And from 20 kilohertz on up to infinity into the millions of hertz, the megahertz, we're now talking about things that we cannot hear. The one thing you'll notice as I work through these slides is that the wavelength of the signal, that signal got longer in the lower frequencies and then shorter in the higher frequencies. And what that means to us is that as we go higher in the, how do we get rid of this? Exit. As we go higher in the frequency range, that wavelength becomes shorter and shorter. Well, the shortening of that wavelength produces three characteristics of ultrasound, which makes it very useful for us as condition monitoring technicians, as people looking to find different problems with assets. The first of those characteristics is distance. I hope those lines aren't going to stay on here the whole time. There we go. Well, we'll just put up with them. So the first thing is distance. The lower we go in the frequency range, the longer the distance that sound will travel through the medium, whether that medium's the earth or the air or through steel or whatnot. As we get into the audible range, the distance that sound will travel before it's attenuated and absorbed is significantly shorter. And when we get into the ultrasonic range, the distance becomes even shorter yet. And so these characteristics are something that are very useful for us because when we're trying to find the source of an ultrasonic signal, we don't want to be interfered with by competing signals from other assets. So if I'm focusing on a particular spot of a substation, I want to focus just on that spot, and I don't want to hear ultrasound from other competing areas. I'm just going to restart this because those. There we go. Well, they're still there. The second characteristic of sound is directionality. So when we listen for infrasound, the directionality is 360 degrees. The sound is traveling in every direction. As we get into audible sound, this is not a Pac-Man. It's to display that if the sound source is here, that the signal becomes more narrow and more focused. If you're ever walking behind a person and that person in front of you is speaking to you, but they don't turn and face you, you have a more difficult time hearing them because the sound that they produce doesn't want to go backwards, it wants to go forwards. It doesn't want to go backwards to where your ears are. Well, as we go higher and higher in the frequencies, that directionality becomes even more so. So when we get into the ultrasonic frequencies, we start to see that if we look at this little pie shape here, that's the path, or that's the direction that ultrasound is going to travel through the medium. That directionality makes it very good for us to use ultrasound to pinpoint the exact source or the exact location of the signal. The third aspect of ultrasound propagation is boundary behaviors. So ultrasound, unlike the bass sound from a subwoofer, for example, doesn't want to stay inside. You know, a subwoofer in the trunk of a car is going to boom, boom, boom. It's gonna pass through steel and pass through windows, and we're even gonna feel it before we hear it. But ultrasound that's produced inside of a body, say inside of a transformer, for example, or inside of a switchgear panel or an electrical cabinet, that ultrasonic signal is going to stay inside that containment until we put a contact probe or some kind of an ultrasound sensor or a waveguide to draw the signal out and into our instrument. So again, that's a very good characteristic for us when we're trying to locate exactly where a signal is coming from, as you'll see in one of the case studies. We like to say that ultrasound owns the apex of the P to F curve. And I'm just going to let this diagram run now. So the P to F curve is designed for us to understand from the point of D, design, to I, installation, to P, potential failure, to F, functional failure, when an asset is degrading to the point of that functional failure. And as condition monitoring technicians, our job is to keep this line as straight and flat for as long as possible. And to do so, we use technologies like ultrasound, like vibration analysis, audible noise, heat thermography, oil analysis, lots of different condition monitoring technologies to help us understand when our assets need to be maintained. Ultrasound sits here, just past the potential failure. So in other words, as soon as a new asset is commissioned and starts doing its job, ultrasound plays the earliest role, or gives us the earliest indication that the condition of that asset has changed. So we can rely on ultrasound to be our first line of defense against asset failure. We like to say that ultrasound gives us asset fitness, and we emphasize the word fit as part of the word fitness because the three symptoms that we can detect, or the three sources of ultrasound, come from friction, rubbing of components together, impacting when components are banging against each other, and turbulent flow, such as leakage or partial discharge, where the air molecules are disrupted in creating this turbulence. Well, all three of those, friction, impacting, and turbulence, produce ultrasound and are therefore, ultrasound is a good fit to help us find those exact symptoms and know when things are going to fail. From that, we've discovered that there's 8 application pillars for ultrasound, and those are on the screen there: mechanical, leaks, lubrication; electrical, which we're talking about today; valve inspections; steam trap inspections; hydraulics; and tightness testing. I'm not going to spend time going into all of those, other than to say that each one of those produces either friction, impacting, turbulence, or a combination of all three. Especially with electrical systems, we're looking at turbulence, which is produced by partial discharge. If I reorganize those and I look on the left at leaks, valves, steam, and tightness, I can learn how ultrasound can help me eliminate waste. And by eliminating waste, I also can help my company achieve its sustainability initiatives and just help make the planet a better place. If I shuffle them again and I put lubrication, valves, steam, electrical, and hydraulics and mechanical as my priorities, now I have the power to eliminate unplanned downtime from all 6 of these. And when I can eliminate unplanned downtime, that means that all my downtime is planned. And when my downtime is planned, it enables me to work safely. When I work safely, I eliminate workplace accidents. So ultrasound helps me contribute to a better environment and a better planet. It helps me plan our downtime, so that helps us be more economically viable. And most importantly, ultrasound helps us to have a safe workplace. So that's your ultrasound 101. That's the 30,000 foot view. If you ever take a category ISO Cat 1 training from us, those few slides takes more like a half of a day to cover through. But those were the highlights. Those are the things you really need to know just to connect the dots on the rest of this presentation. The importance of reliable power systems. Well, we can put that in a lot of different contexts. Reliable power systems help keep the lights on. They help keep motors turning. If you're in a hospital in the ICU, they help keep the medicine dripping. If you're working in an institutional building or commercial building, they help keep the air conditioning running. When we don't have reliable power systems, we have darkness. When we have darkness, it really emphasizes these 4 darn lines that I can't seem to get off of my screen. I'll figure it out probably when I get off this call. But they're there for the duration, so let's just live with it. So that is, my friends, the importance of reliable power systems, is making sure we can keep the lights on and keep everybody happy, safe, warm, and comfortable, and keep our manufacturing plants making things. Electrical failures often start small and then they go unnoticed until it's too late. And again, that plays right into the sweet spot of ultrasound, because ultrasound detects microscopic, or I like to say microsonic signals, which only tell us that things are starting to go bad, but we still have a big window to make them better. Unreliable assets are dangerous and inefficient, and they add stress to our already aging infrastructure. Let's talk a little bit about the National Fire Protection Agency's mandates to help protect people and to protect assets. These are electrical safety standards which focus on reducing risk. The first one is known as NFPA 70E, and the E on the end denotes that this is a standard that was written to protect people from electrical hazards. This is essentially the electrical safety code that your electrician follows when he comes to do work in your plant or in your home. And they establish safe work practices to prevent shock, arc flash, and arc blast. They define approach and arc flash boundaries. They require hazard identification, risk assessment, and control measures. They specify what personal protective equipment we need to choose, how we work our lockouts and our tagouts, and what training people who are working on or around electrical assets must undergo. All of the NFPA 70E aligns with the OSHA electrical safety requirements. NFPA 70B, on the other hand, is a guide for maintaining equipment for reliability and safety. So this is playing into the hands of condition monitoring technicians. This is what's helping us as those technicians, as those reliability engineers, to maintain our equipment. And in the most recent edition of NFPA 70B, there has been some dramatic language adjustments, which if you're responsible from a management point of view on electrical assets, you really need to know about these. NFPA 70B defines electrical maintenance programs for assets. It promotes preventative and predictive maintenance practices. And I'm going to say that the word promote is now been upgraded to mandates, because preventative and predictive maintenance practices are now required. It's the documentation that those practices are in place are now a requirement of all the inspections and tests that you do, whether you're doing in-house infrared thermography or outsourcing it, or ultrasonic scans or any other types of tests. These are mandated tests, but you also need to, in the event of an inspection or an audit, prove through documentation that you're doing these. NFPA 70B serves as a complement to NFPA 70E by ensuring equipment is in a safe operating condition always. And I won't, this is just a summary slide, and I think these slides will be available to anybody who wants them. But basically, this table just gives us a comparison between the full title, the primary focus, the objective, the key theme, and the target audience for both 70E and 70B. So let's not spend more time on that. So let's jump into understanding what partial discharge is. First of all, in simple terms, it's the most common early failure mode for electrical systems. It's a localized electrical discharge that occurs within insulation systems, but it's a discharge that does not completely bridge the electrodes. In other words, it can be caused by dirt, by corrosion, by a gap, and it means that the dielectric material or the insulation hasn't yet failed, but it is in a deteriorating, degrading state. For ultrasound inspectors, partial discharge is the first audible clue. It's actually an inaudible clue that an electrical asset is under distress. We write audible in the slide because ultrasound has that superpower of taking the inaudible and making it audible, thus giving us superhuman hearing. Ultrasound provides early detection and helps us prevent full-on insulation failure, which can result in a more catastrophic event, whether it be a fire, a transformer fire, an explosion, or an arc flash or an arc blast event, which we obviously want to avoid. So what are some of the causes of partial discharge? Well, partial discharge occurs when the electric field strength exceeds the insulation's ability to resist ionization. The causes include voids, cracks, contamination, sharp edges. They're caused by poor workmanship typically, but also by moisture, corrosion, and aging. The one critical thing that we all have to remember or all need to know is that partial discharge, once it starts, it begins to accelerate its own damage. So partial discharge in itself doesn't manifest itself out of thin air. It happens because the dielectric material is beginning to break down. But once that partial discharge is there, the ionization of the air molecules around the partial discharge field produces gases which are, let's say, corrosive, let's say not friendly. So they start to accelerate the damage to the insulating material. Well, the answer to this question is all over. The partial discharge is present in most medium and high voltage systems. Anywhere where insulation might be aging or where it's stressed. Switchgear, so we're going to have internal corona and tracking and eventually arcing inside of electrical cabinets, motor circuit control panels, those types of things. In a lot of the cases, partial discharge is enclosed in a cabinet, so it's not obvious for infrared thermography. If the partial discharge does in fact generate heat, which most often it does not, even if there is a direct line of sight, which is what infrared thermography needs, there's not always going to be heat. But when partial discharge is enclosed inside of a cabinet, well, it's ideal for non-intrusive ultrasound inspection. Another place where partial discharge hides is inside cables and joints, especially if you have cables that are bending. We try to keep our cables, especially our medium and high voltage cables, as straight as possible and as short a lengths as possible. So any bends in the cables compromises the material structure of the insulation, and that's where partial discharge begins. Transformers and bushings, line bushings, connections on phases. The internal voids there can allow for partial discharge as well. And then VTs and CTs, surge arresters, capacitor banks, lightning rods, those types of things. Ionization is what is produced when you have partial discharge. It forms ozone and nitrous oxide, which combines with moisture to produce nitric acid. And if you look here around these cables and around the outside of this, anywhere where the cables are touching or where the cables are touching an insulating material, or in this case, just the channel, you have that white powder right where my mouth is, and that white powder is a visual sign that there's some partial discharge activity going on there, which is going to further lead to corrosion and insulation deterioration. Looking at that same image with an infrared with a thermography camera, well, it may not produce detectable heat. And this one definitely did not. As you can see, it's just cool colors around that internal corona discharge. But it eventually is going to lead to flashover and fires. Then you'll have heat, but then you don't have a window to detect it. So these types of problems are detected early with ultrasound. We can run routine inspections and routine maintenance and plan to have these assets either repaired or replaced. Again, that white powder that we see at the site of a corona, if you look at these medium voltage cables, again, where the yellow circle is, we can see the white powder. And again, we don't want to have these cables touching each other. The ionization of that air around edge energized conductors typically only occurs above 1 kilovolt. Typically, we will not produce enough heat to be detected with an infrared camera. But when we detect them with ultrasound and we look at that ultrasonic signal, because we can record it, when we look at that ultrasonic signal in either the spectrum, the FFT, or the time waveform, we see consistent amplitudes and repeating patterns. Depending on where we are in the world, we'll also see 50 or 60 hertz harmonics, which are indicative of the line frequency. So, and here's a good example of the time waveform. And here's what it sounds like. Just a classic buzzing signal. But when we take this time waveform, this is 2 seconds. This is basically, this whole time waveform view here is just 1 second, 1 second of data. So we've really expanded it out, and each one of these bursts is correlating to the line frequency of that electricity. So that's corona. Tracking is a whole other kettle of fish. It's another term. It's a term that we use to encompass surface discharge across contaminated insulation. And so if you look, this middle picture is really the best one. You see all of this branching out. And this is surface discharge, and it's forming a path through the material to ground. It's trying to find a path to ground. You get this crackling, sizzling sound if you're using an ultrasound detector to find it. In the, you won't see a whole lot in the FFT, because FFTs, or spectral analysis, is really designed for repetitive events, and tracking tends not to be repetitive. It tends to have intermittent bursts. In the time waveform, also bursty and uneven amplitudes. And tracking can occur at any voltage. So this is what I mean. Here's the time waveform. I'll play the sound for you in a second, but what you see is you see here, you see bursts, and then it's quiet for a little bit, and then more bursts of energy. And this is typical of tracking as it's making its way through the insulating material. So here's a real live look at a bus bar inside of a switchgear cabinet. And what we can see here is we'll just draw your attention to the actual carbonized path of the discharge, this branching this way and branching this way along the surface of the bus bar. If you look up here, you can see dust, you can see dirt, and we just move the mouse over to there, we see that faint purple glow, and that's indicating active arcing, surface discharge. You might not be able to see that with your eye because it's behind a cabinet. We've opened the cabinet after we safely opened the cabinet after we detected it. You also might not see any heat from that unless you have a direct line of sight to it. When you have dust and debris, you have increased surface conductivity over time. And so here we can see that an example of an external surface discharge progressing towards arcing if this isn't detected in time. I would say that this was not detected in time, but it really is, it's relative. It's contextual. I mean, the asset's still functioning, so we don't have an outage, but it's deteriorating. I don't think that this can be fixed. It needs to be repaired. That means we have a longer repair time that is more than just blasting some dry ice or something in there to a little dusting and cleaning. This isn't simple maintenance anymore. This is going to require a planned shutdown. So it would have been nice to detect this sooner than where we're at now. This is a time lapse of the formation of surface tracking. So let's just start playing it now. And don't ask me, I don't know how long this experiment ran. This is a lab experiment, but you can see that this is the process of surface tracking generating and slowly gnawing its way through the insulation material. And then when those two connections join up, electricity finally gets what it's thirsting for, and that is to find its path to ground. That's all it's trying to do, is find a path to ground. Here again, we're inside of a glass tube, and we've obviously sped things up, but we can see that once that partial discharge starts, there's no stopping it, and it just continues to evolve and continues to eat itself from the inside out. Here is some partial discharge that we detected inside of this high voltage cable. And you can see the damage that was done because it was not detected in time. It turned into a cable failure and a fire. The third progression of partial discharge is arcing. So we started with corona, which is really just nuisance sometimes. We've progressed to tracking. Now we're at the stage of arcing, where we have high energy discharge bridging the conductors. Remember, early partial discharge, the discharge does not bridge the gap between conductors, but with arcing, it actually bridges the conductors or finds a path to ground. Again, you're not going to see anything in the FFT or in the spectrum. It's broadband, it's chaotic, it's not sinusoidal. In the time waveform, we're going to see exactly what we see here: sharp, audible, violent bursts. In the ultrasonic condition indicators, we're going to have a high crest factor. So that's looking at the impacting or the high spikes of voltage like we have here and over here, versus the overall noise, the RMS of this whole signal. And this is an immediate safety and reliability risk. If this is going on inside of a closed cabinet, there's a good chance that there's a buildup of combustible gases. And when you open that cabinet, you're going to have an inrush of air. That air is going to mix with the gases and the arcing, and you're going to have yourself a quick trip to the sun because an arc blast has temperatures on par with those at the surface of the sun. So we don't ever want to be in that situation. Even if you've got the best PPE in the world, you have a high risk of not walking away from an arc flash or an arc blast. Ultrasonically, that's what you're going to hear. And when you hear that, it's time to call somebody. It's time to shut things down. Electrical inspection with ultrasound, the best practices. So infrared and ultrasound, you want to use ultrasound in between your annual infrared scans. Or if you're going to do an infrared scan and you want to open up a panel or you want to open up a cabinet, then do an ultrasound scan around the cabinet prior to opening it up for the infrared inspector. So you have a higher level of confidence that there's nothing going on inside there that could create an arc flash or an arc blast. And of course, you got to be suited up. If you only use infrared, you may miss conditions that infrared cannot see, or you may miss conditions that don't produce heat. Our recommendation is to use infrared and ultrasound as complementary technologies. One sees what the other one can't hear, and one hears what the other one can't see. And then finally, to analyze the sound files in the frequency and the time wave in order to diagnose exactly what the problem is. So this transitions us from ultrasound 101 to electrical maintenance to the SDT product of ultrasonic solutions. And we have a host of them here. Most of these can be quite useful for inspecting electrical. The SDT 200, the 270, and the 340 are all great handheld devices to carry around for switchgear inspections, for connecting parabolic dishes or long-range sensors so that we can hear problems from the safe side of the fence. Here we have what we call the SonaView, which is an acoustic imaging camera. This camera has 112 digital ultrasound sensors, as well as a long-range, high precision camera. So with the SonaView, we can take a picture of an electrical asset, and if there's any kind of partial discharge, tracking, or arcing going on, you'll see right here where my mouse is encircling, you'll see a little burst. And that little light burst says that that's where there's a source of ultrasound. That part of the asset needs to be inspected. So this is a great little camera for walking transmission and distribution lines, for listening for corona discharge, or standing on the safe side of the fence and taking a visual, either images or video of a substation or any assets where you can't get close. The Vigilant is a permanent system. We've sold quite a few of these in Asia Pacific, specifically in Indonesia, but also in Thailand. And what we're doing with these is we're putting airborne ultrasound sensors inside electrical cabinets, and then we're cabling them back to the Vigilant. And the Vigilant is doing a 24/7, 365 analysis, or let's say just a monitoring of those cabinets to be sure that there's no changes in their condition. We've also connected contact sensors to the outsides of oil-filled transformers. And so with the Vigilant, we can put up to 8 sensors onto a transformer. So we can have airborne sensors pointing at the phases. We can have contact sensors listening for partial discharge inside of the oil. And this becomes a total 24/7 system for monitoring transformers. A couple of different contact sensors. So this sensor here in the middle, the RS2T, this sensor here with a threaded mount or either a magnetic mount gets stuck directly onto either a switchgear panel so that we can hear through it, or it gets permanently mounted on a transformer if we're doing any kind of long-term condition monitoring on that transformer. Our airborne sensors, so the flexible sensor here in the bottom left, that's very useful for scanning around the seams, any air gaps in MCC panels, in electrical cabinets. It allows us to hear what's going on inside of them. And then this up here in the top right-hand corner, the Paradish 2. The Paradish 2 is very useful for long distance inspections of transformer and transformers, and as well as transmission and distribution lines. Give you an example of that. Here on the right, we have our junior technician. Not a lot of experience or skill required here, but he's got himself some headphones connected to an SDT340 ultrasound detector and a parabolic dish. And this parabolic dish has a laser dot on it, so we can scan around the phases of this transformer and figure out if there's any potential hotspots. So that's easily documented. You take a picture and say, we know exactly where the problem is now, and that gets into a work order for future maintenance. Look at a couple of case studies. So we have one here, so an electrical inspection. This is a high voltage transformer, and we inspected it with ultrasound. We used the SDT340. To refresh your memory, that was this guy right here on the right that gives us the time waveform view right on the screen. And so using the 340 with the flexible wand attachment, and again, the flexible wand was this fellow right here. And the signal that we heard through the air gaps of this ventilation at the bottom, well, we took those into the FFT, and lo and behold, here we can see the 1, 2, 3, 4. We can see all of these harmonics, and these harmonics are all lining up with 50, 100. Oops, lost my picture. These are lining up with the 50 hertz. You can see them over here. So number one is at 100 hertz. 2 is at 200 hertz. 3 was at 300 hertz. These are all harmonics of the line frequency of this system, which is obviously running at 50 hertz. And I just said that. The recommendation was to perform a cleaning on that part of the transformer to see if the amplitude of those harmonics decreased, or better yet, if they disappeared altogether, which is what we want. Another typical inspection here is a commercial three-phase pad-mounted transformer. And using a contact probe on the outside of the transformer, we were able to pick up the sound of ultrasound, the sound of electrical problems. So we had somebody qualified to open up the panel for us. Once the doors were open up, we were from a safe distance with the parabolic dish. We looked at the left insulator, the middle insulator, and the right insulator, and this is what we heard. So the left insulator is pretty quiet. We can hear that it's quiet. We can also see in the this time waveform that there's very little activity there. So if we move over to the middle insulator, you can see that there's a lot more activity picking up here, and that the sound has become, the amplitude's grown. And if that, just for a second, I'll take you back to the early slides here when I talked about distance, right? Distance and attenuation of signal through the air. So in the ultrasonic range, as we go higher in the frequency range, that attenuation happens. And this is why when I'm pointing, also the directionality of the signal, if I'm pointing at this phase, I'm not going to hear what's going on in this phase because ultrasound is much more directional than audible sound. If I move over to the right insulator, I can now see that the amplitude of my signal has dramatically increased. And just to go back and look at the scale here, the scale of the y-axis is 1,000 microvolts. And it's also 1,000 microvolts here and 1,000 microvolts here. So we've intentionally scaled all three of these time waveform views with the same y-axis, so that they're, it's comparative across. And we know with no uncertainty, zero uncertainty, that the problem is coming from this third phase. And now, again, this could be very early in the failure curve. And if it's early in the failure curve, it could be simple maintenance. It could be some dry ice cleaning. That's all we need to remediate this and get it back to working. When I take that signal from the time waveform and I put it into the spectrum, I just happen to have it at in CPM instead of hertz. So if I want to take that, like if I look at the first signal here, it's 3,600. If I divide that by 60, 36 divided by 60 is 60. 3,600 divided by 60 seconds is 60 hertz. So that's, I know that this is, that each one of these harmonics is part of the line frequency of the voltage. So I know that this is only partial discharge. It hasn't advanced to tracking yet. It hasn't advanced to arcing. So I know that I'm very early in the failure curve, and that simple maintenance is something that's going to probably cure this problem. Yeah, and that's the text is what I just said. So I'll just push on. 2000 kVA transformer. Again, inspecting through these vents using an SDT340 and a flexible wand. An absolutely horrible sound. The only thing I could think of worse would be running my fingers down a chalkboard. Just to correlate, we also took an infrared thermography image of this same transformer using our FLIR camera, and we can see clear hotspots. We know where the problems are. So again, this is a case where we can use both ultrasound and infrared thermography as complementary technologies. Just a quick word on the SDT340 then. It's a multifunction data collector that has the ability to have sensors plugged in to make it airborne ultrasound, contact or structure-borne ultrasound. In addition to that, we can plug in a vibration accelerometer. This gives us the ability to listen to and take data off of rotating equipment, such as cooling fan motors and other, water cooling pumps and those types of things. We can collect temperature measurement, and it also has a tachometer built into it. It has an internal database, and it reports to software, which allows us to do measuring, trending, and analysis. So all of those earlier images that I showed you of time waveforms and spectrums were all collected with the 340 and then analyzed in its software. And this can be applicable to transmission and distribution lines, substations, switchgear, motor circuit controllers, transformers, and much, much more. Because we can look at the time waveform here and the FFT on the screen, it's actually not a bad little tool for doing an on-screen and in-field analysis. And again, it's compatible with the UAS3 software, which here's a simple screenshot. And if I wanted to build an asset tree on the left, of all of my electrical assets and all the measurement points on my electrical assets. Say, for example, I have a switchgear room full of electrical cabinets, and each one of those cabinets has a unique identifier. I could build an asset tree and name each of those unique cabinet panel numbers. And then I can just send somebody out, and it doesn't need to be a Cat 3 Vibe person. It could just be a junior technician can go out, put his sensor on each of the panels, and then collect both a time waveform, an FFT, and a static trend data. And I can start to build a measurement database, or let's say a condition monitoring database of all of my electrical assets. So what does this do for me? Well, it allows me to build that centralized database where I can organize my inspection routes and create a recorded asset history. I can have different dashboards that I can make for my own purposes, and I can do the advanced analysis with a time waveform in the spectrum. But what's not mentioned on this slide, and maybe the most overarching point, takes us back to NFPA 70B. If for some reason I have an audit or an inspector come in and audit my facility and say, show me that you're following NFPA 70B, I need to see a documented proof that you're doing all of the right things. I just need to open up my computer and show them this database, and I can pull some reports out. And just like that, I can say, yes, sir, I am following this to a T, and I am in compliance. Okay, SonoView acoustic imaging cameras. Again, 112 digital MEMS sensors, which are on the opposite side of this camera. And they're arranged in a precise configuration to deliver high sensitive detection and distance. So we have a very, very narrow range of focus, but we can detect problems up to 150, even 200 meters away. And I love that because that keeps me, again, on the safe side of the fence, especially when it comes to substation inspections. There are onboard diagnostic features. So in addition to capturing an image that clearly shows me where electrical activity is happening, or a video, I can also look at the PRPD graph. PRPD, if you don't know, stands for phase resolved partial discharge. And that phase resolved partial discharge looks at different phases of the complete cycle of a signal. And I can use that to determine whether or not, or what type of electrical fault I've just discovered. This SonoView also has GIS integration. So if I'm out doing transmission and distribution line patrols, and I log a defect, I can later go back into my report and use my GIS integration to know exactly where I was, and I can map where all of my defects are. Nice feature. So here's a typical image, all right? On the top, I've got just a basic, looks like a polyceramic insulator on the middle line of this medium voltage residential line, but I can see from that color burst that I have a partial discharge activity. And my PRPD graph is here. And I can see from that PRPD graph what type of defect that is. And this PRPD looks completely different from the PRPD graph on this transformer. And again, also this image doesn't really show that well, but it was cut off on the bottom a bit. But again, another line insulation issue here. So let's take a look at the three potential fault patterns that we can detect with the AI in the SonoView Plus. First of all, when I have just a single burst like this is the full phase. The single burst here tells me it's corona partial discharge. When I have a double burst, it's surface partial discharge. And when I have a more of a pattern like this, it's floating partial discharge. And so the difference between surface partial discharge and floating partial discharge, this is just another language for corona, tracking, and arcing. So we recommend at SDT to have a multimodal strategy. We want you, obviously, this presentation emphasized the strengths of ultrasound. This is by no way or means me saying use ultrasound and ultrasound only. A full and effective condition monitoring program for medium and high voltage electrical assets combines infrared thermography, transient earth voltage, digested gas analysis for full coverage. We want all four of those technologies used. Each of those methods is supported inside of the NFPA 70E for safety and 70B for condition monitoring and maintenance. We want you to use ultrasound first as your first line of defense to screen. You use the others for confirmation, but the screening that something exists, something hidden exists, produces a level of safety for you. When we have correlated data from 4 different technologies, we have better prioritization for planning the maintenance, and we get a quicker ROI on our NFPA 70B maintenance and condition monitoring strategy. When we can have evidence converging from multiple technologies, we can make more confident decisions. And when we can make more confident decisions, ultimately we lead to a more safer facility. And again, I'm going to end this out with this slide here, which shows us just a table. So down the left side, we have the asset type or the asset fault. So switchgear, internal partial discharge, overhead lines and bushings, transformers, cables and terminations, and resistive joints and loose bolts. So we can see based on the technology that you use, whether it's ultrasound, infrared, ultraviolet, TEV or transverse voltage and radio frequencies, and DGA. So we can see where each of those technologies excels. Ultrasound has 4 check marks out of 5. The others have fewer. I think the biggest check mark here goes for early detection. And early detection for me means, and I know I'm repeating myself, but what early detection means for me is knowing that I've got an earlier window to plan my maintenance strategy. I've got an earlier window of detection means that I'm not having collateral damage, because remember, when you have partial discharge, what happens is it starts to accelerate the decay. So the sooner I detect it, the earlier I can prevent things from spiraling out of control. That pretty much wraps up. I mean, I've run out of slides. I can talk forever, but I don't have any slides left. So I think I'm going to stop it at this point and turn it back to see if there were any questions that this may have raised.
Okay, thank you very much, Alan. Excellent
My
presentation, as always, appreciate it. I have some questions. When you mentioned AI, it was about imaging, but I was thinking it was going to be about AI. And so it brings up the issue of AI integration. So how do you see AI improving the interpretation of ultrasound data, especially distinguishing between corona tracking and arcing? And
Right.
what are the implications of AI integration? What are the opportunities? What are the challenges in general? What's your opinion of this? Because it's not only for your presentation. I'm going to ask the same thing to Drew in the next presentation about their testing and monitoring and analytics and all of that. So maybe you can address that first.
100%. So, AI is a buzzword or a buzz acronym, artificial intelligence, and our marketing departments. I'm actually thinking of giving our marketing department a little pepper grinder with AI written on it, and they can put a little bit of AI on everything that they put out the door through our website. But I mean, it's one of those things we're talking about today only because the computing power has gotten so strong. But in reality, AI has been around for a long, long time. AI is just an acronym or it's a synonym for pattern recognition.
Hmm.
And in order to recognize a pattern, what do we need? We need to have data. And so for me, for ultrasound and applying AI to ultrasound, it really boils down to where can I get more data to put into the model, and is that data reliable? Is the data clean? And you can have too much data as well. But the whole idea of that is to bring that data in and put it into a model that can make sense of it. For us with the SonarView, we're looking at these three basic images, and these are just representations. But I think if I go back a slide, let me go back to
Acoustic imaging. That's what I
yeah,
saw.
yeah, here. So
Uh-huh.
we've got this phase resolved partial discharge representation on the screen. And each one of these patterns is depicting a different phase of deterioration in the insulation. So what we're doing is we're training our AI model to recognize, because no two, they're like snowflakes. There's going to be no two the same, but they're going to be similar. And so the more we can feed into the pattern recognition, the more confident we can be in saying that this is corona, this is arcing, this is surface discharge. And so that's really, we're at the stage now where if I go out and I scan 1,000 assets in a substation and I generate my report, that report is going to have a label on it that suggests what it believes the problem to be. And that's all related back to the pattern recognition or the artificial intelligence looking at that image. And so that's really where we've developed it.
So what are the opportunities? What will it provide to you and provide to the user more than what they already have? What difference will it make in the end?
Confidence.
Confidence, is that the most important thing?
I think so. I
Yeah.
think so. When you think about what your job is as a reliability technician, your job is to go out there and spot a defect early enough in the deterioration phase to say this needs to be shut down or this needs to be maintained. And you can get 9 calls right and 1 call wrong. And what are they going to remember?
Hmm.
The one bad one. So I really think confidence plays a big role in knowing that you're making the right decision, because it's not just you that you're impacting. You could be impacting production. You could be impacting productivity, especially if you make the wrong call. And what's worse is, you make a call, they shut it down, and there was nothing wrong with it. Well, that's bad enough. But if you don't have the confidence to make that call, and then it goes the other way, and you end up with a fire or a transformer explosion, well, or worse than that, something that hurts or kills somebody. I want confidence. I definitely want confidence in that
Okay.
decision. Yeah.
Do you envision AI eventually guiding real-time decision making in the field, such as recommending cleaning, repair, or immediate shutdown based on detected patterns?
I absolutely do.
Yeah.
Um, I absolutely do, but I would just again highlight the one thing that I said, that ultrasound owns the apex of the P to F curve. So we always keep in mind that what we are able to find with ultrasound, especially if we're using it as routine maintenance or regular maintenance and monitoring, we're finding problems early enough in the failure curve that we still have a large window. Very rarely do I go out and find a problem with ultrasound and have to hit the emergency stop button because it's so early in the failure curve.
Hmm.
But yes, to answer your question, I definitely see us getting to that. We're already to that point now with our AI models for for rotating equipment. So getting away from electrical assets, we're collecting data off of bearings, gearboxes, and that data can tell us if the problem is misalignment, if the problem is lubrication, if it's a broken tooth on a gear, cavitation. All of these problems are being identified now by AI. And then we're coming in with Cat 3 and Cat 4 vibration analysts and confirming that AI was right because it's still early.
Mhm.
Yeah,
Does does your model need to be trained?
absolutely. So
Yeah.
again, it's pattern recognition. And if any of you have ever played a sport, you've heard the term practice makes perfect.
Hmm.
If you've played a high level sport, you'll
Yeah.
know that that doesn't apply. Perfect practice makes perfect. So if you're
Right.
training your AI model with bad data, then you're poorly trained. If you train yourself to shoot a free throw in a basketball court with bad form,
Hmm.
you're not going to get any better. So the same with our A models. We have to train them, but we have to have good, clean data.
Okay. Good answers. So really, it's a really important question these days. Yeah, I know that
Absolutely.
AI is everywhere. They're
Mm.
talking about it. Well, I'm focused on trying to provide information about the misapplication of it or the poor expectation for it, and the responsible use of it as
Right.
a tool and not as a substitute for like training and what we're talking about. Okay, next.
I think
Yeah,
it's, sorry, I just add,
go
no,
ahead.
I'll just add to that point is I think it needs to be seen as an efficiency tool and a
Hmm.
confidence tool.
Right.
But I think too many people are using it as a tool to make them lazy so they don't have to do the work. And that's really not what it's there for.
Well, humans are lazy. Well,
I
that's
hope it,
okay.
I hope
If
AI
the
doesn't make us
predictions are
lazier.
true, humans will be replaced by AI, and then there'll be no more laziness.
Repurposed.
Repurposed. Oh, that's correct. That repurposed. Okay, next question. Can data be printed from the device? This is from Richard. I don't know exactly what device he's talking about, but maybe you do. Can data be
100,
printed from the device?
absolutely,
Okay.
absolutely. So, I mean, I don't want to jump out of this and go into a report, but
Yeah.
what you see on the screen here are three images that we
Right.
captured during a routine inspections of electrical assets. These images are saved to the device. We can also save videos, but the images are all uploaded into a cloud-based reporting software. And from there, a report is generated and as a PDF that you can either email or print out. And so what you'll have is you'll have this image, you'll have the data that's on the screen here, and then you'll have some recommendations. And then you can go into that report and make your own
Right.
annotations. Yep.
Okay, here's another question. Can you share an example where you detected a failure that other technologies completely missed?
I think I already did in this
Yeah.
presentation,
Okay.
but
That's
yes,
that's
yes, I
fine.
could for sure.
Okay. Uh, and then another question here. What is the range of cost of the devices? I
Yeah.
don't know if you want to talk about pricing in this format. Maybe you can contact these people afterward with questions like that, but
Yeah.
I don't know what you feel comfortable with.
Well, I don't, I've been doing this too long to be uncomfortable then. You can certainly share my email address in the chat with
Right.
anybody that wants to reach out. But just to give
Okay.
you an idea, if we go back to this product family here, where is that slide here? We're looking at anything. We're looking at a range from about 3,000 US dollars up to 20 to 25,000 US dollars. All really depends on
Well,
on the
okay.
on the tool and the solution.
All right. That's a big range. Okay. What training is recommended for technicians to accurately interpret the data?
Yeah, good question as well. Training to me is the most important thing. If what I've seen over my 35 plus years is that the programs that succeed also invested in training. They didn't just buy an instrument and, it's like gym, your fitness equipment in your basement. I mean, it rarely gets used except for maybe hanging your clothes to dry. A real fitness program requires a trainer, a personal trainer. And I believe an ultrasound program also requires a personal trainer. Now, the standard, the global standard for ultrasound training is ISO 18436-8, a standard that I participated in helping formulate through the Standards Council of Canada. And that is a 32-hour course, but it doesn't just cover electrical, it covers, all of the application pillars I talked about earlier. But it's the most important thing. This stuff, you're going to buy this stuff and it's going to sit on the shelf if you don't train people on not only how to use it, but the importance of using it.
Sure. Okay. Well, that was an excellent presentation. Thank you very much. Appreciate it. Again, you do good work when you do this. Thanks very much.
Appreciate that.
Okay. Yeah, no problem. Okay, so thank you very much, and we'll move on to our next presentation, which is from Drew Welton at Intellerent. Okay, great. Drew, are you there? Oh, there he is. Okay, if you would, let's see, I need you to activate your microphone. I can't hear you. Something's up. Yeah, the Zoom's Drew, the Zoom says that your microphone is activated, but we can't hear you for some reason. All right. Maybe in the audio settings you need to choose your headset. Oh, I see you nodding there. Okay. That'll work. Did that help? I sent you a message to unmute. Yeah. No, can't. Okay, let's take a break for a few minutes and have Drew sort out his headset there, and then we'll continue.
Looking for the settings. Can't find the settings.
I can hear you now. Great.
Oh, you can. Okay.
Yeah, everything's fine now. Okay, well there you go.
go.
All you have to do is plug in the headset and it'll work fine. Okay.
Oh, very good. So
Okay,
you can see my screen, okay, right?
Yeah, everything's fine. Your screen's there and everything. So the next presentation is titled Transformer Protection Settings. How confident are we? Good title. I'm looking forward to this. Okay, Drew Welton is making the presentation. He's Vice President of Business and Technical Development for Intellerent. Drew's a regular speaker with us. Glad to have him back. Drew is Vice President of Business Development, as I mentioned. Leading strategic growth initiatives by identifying new business opportunities and forging partnerships and overseeing the development and implementation of technical solutions for the company. So I'm really interested in this presentation as always. So please take it over.
Oh, thank you very much, Randolph, and sure is a pleasure being back once again. So I came up with this presentation for a number of reasons, and I think probably the most, and I think our last speaker talked a lot about reliability, and reliability in the protective relaying world means that the relay does what it's supposed to do in the event of a fault or some type of event that would, activate the relay to give a response. The other half of that is called security. And security means that in the relay world that we're not going to trip when we're not supposed to. So there's two important terms that we have to consider when we talk about protective relaying. So over the past decades, both reliability and the stability of these critical assets has improved with digital technology. I mean, we have, in most all cases, in any new application, moved on from the old electromechanical days to the digital relays. And with digital relays, we don't worry about things like calibration. We don't worry about contacts going bad, or the things that we were concerned about with electromechanical relays. But one of the things that, if you look at statistics that show why relays fail, and we're talking about modern digital relays, the biggest reason is because they're not set properly. And by setting, I'm not talking about just pick up and drop out and time dials of a certain protective element, but also the logic and the configuration of these devices as well. Because the more protective elements you put into a relay package, the more the more chances are that something didn't actually get set properly. And sometimes in the commissioning process, that's hard to find. So I want to kind of focus on transformer protection, because I think this is one of the areas where I see most everybody gets involved if you're into relay testing, or if you're a relay engineer that does settings. We're going to kind of give some examples of where that process can go wrong and how to find it before before something bad happens, like a nuisance trip when you go to energize the relay. So we'll look at two examples. Not all digital relays are the same in terms of how they're set or how they look. They can vary quite a bit, even though they're both doing the same job in protecting our transformer. So we're going to go behind the scenes here a little bit and kind of take a look at the setting and the commissioning process. So if you look at a protective relay, multifunction relay for a transformer, you have three protective zones. One for the internal faults of the transformer itself. Now, this is usually done by certain overcurrent relays, but those that we refer to as phase or ground differential relays. So current going in equals current coming out. We know there's no internal fault in the relay in the transformer itself. The other are through faults, and these are transients that actually go through the transformer, something that's occurring outside the protective zones of the transformer itself. And then we have things that are called abnormal operating conditions, and things that just happen, during the normal operation in a substation that can be a challenge or could damage a transformer. So if we look at the one-line protective diagram, this is the one from Beckwith Electric. You'll see here that you have various instrument transformers. You have CTs on both sides of the transformer to measure current going in and coming out. You've got PTs if you have voltage elements enabled as well, which many of them do, to protect from over voltage conditions and things like volts per hertz. But I always categorize the protective relays in two separate sections: those that are proactive and those which are reactive. And the reason I make this distinction is because if you have a phase differential or a differential relay trip that's protecting the transformer, that means you've already got a problem in the transformer itself, because the current should equal what's going in and coming out. And when there's a fault internal to the transformer, that's where the current's going to flow to, and you'll get this difference in current. Okay, so the other which are proactive are those elements which are actually saving the transformer from external conditions, things like volts per hertz that we'll talk about in just a little bit, but something that's going on outside the transformer that could happen to actually damage the relay. And those are proactive type of elements. So what other forms of protection does a transformer have? Well, we have Buchholz relays, we have pressure release valves, we have rapid pressure valves, you know, different types of things that are going on to, you know, fire extinguishing cubicles, things that, you know, if something should happen to the transformer, these items would take the transformer out of service to prevent further damage or catastrophic damage. So here's a one-line diagram from a Schweitzer relay, and there's some things that I want to point out here. And you'll see between the two, they're fairly similar. They're diagrammed out a little bit differently, but the elements are pretty much the same. You have your two sets of CTs, and you have your differential relay monitoring the currents on both sides of the transformer, and then you have some of your voltage and some of your overcurrent relays that are those proactive. But there's some things in a transformer relay that are very, very important to be aware of. First of all, you have a breaker failure element. So if there is a fault and you try to isolate the transformer and the breaker doesn't open, you've got to have some kind of a backup means to isolate the transformer. So that would be breaker failure. Breaker wear monitoring. Okay, Schweitzer relays actually will count the number of times a breaker operates that's servicing the transformer. Event reports, RTD inputs if you want to do thermal measurements, restricted earth fault. SER is sequence of events. So in the event that you do have a fault or a series of faults, it will date and timestamp and give you the values that caused the relay to trip. Loss of potential. Okay, so if you have a VT fuse loss, your voltage elements will become disabled, so it won't nuisance trip, but it will close an alarm. Through fault monitoring, one of the things that's very, very much overlooked when people set protective relays for transformer, and then oscillography. So I'll tell you a little story. I was talking to a gentleman that from a service company, and he was in the field and he was actually commissioning relays on a GSU, a generator step up at a nuclear facility, a very obviously a critical asset in a critical location. And they had backup protection. There were two relays protecting it, as you often see in critical assets. And he got a call in the middle of the night, and one of the relays had tripped on the differential. Okay, so this is not a good thing. So he got in his car, drove out the next morning to the site, and by the time he got there, they had already started to disconnect the main connections to the transformer. They're putting up scaffolding. They got all their test equipment out, and he walked up to the foreman and said, by the way, before you start doing anything, have you looked at the relay and checked the oscillography and the event recorder? And he was kind of dismissive. He said, yeah, no, go away, young fellow. We got to find out what's wrong with this transformer. Well, what was evident here when he started to look at the fault record, there was no differential trip. The relay had actually nuisance tripped, had an internal error on one of the processors. So it's very important that when you set a relay, you set these types of additional functions and capabilities. So in the event that there is a problem, you have the means to look at things. I mean, when I worked for a relay manufacturer, and whenever there was an event or a trip that occurred, they'd immediately call our tech support, and the first question out of their mouth was, did you save the through fault oscillography? Did you save the oscillography in the sequence of events? Could you send it to me? And if they said, well, no, we didn't have either of those two things enabled, well, guess what? There's nothing I can do to really help you decide what it was that happened during that event. So one of the important things that we have to look at when we're setting a transformer differential is how the transformer is connected. And we know that normally between the primary and the secondary windings, you have a 180-degree phase shift, but that can change very easily by anywhere from 3 to 330 degrees, because when you're applying the relay has to know the correct vector relationships. And you can see here that these over here on the left-hand side are actually from the Schweitzer instruction manual. On the right-hand side, we see from the Beckwith. And you can see that not all transformer manufacturers diagram these out or call them the exact same thing. So IEC says you've got a Y connected primary or Y connected secondary, and there's no phase shift between the two windings. So it's just a simple 180 degrees out. When we start getting into, say, a YD1, you have a Y connected on the primary side, a delta connected on the secondary side with a 30 degrees phase shift. So it's important to really look at your transformer nameplate. And that's one of the points that I want to make out. Pretty much every setting that you're going to put into the relay, including the differential, comes from information on the nameplate itself. And sometimes they can be very difficult to read because not all nameplates look the same or are arranged the same. So if you're a person that's responsible for setting or testing a protective relay, you have to understand what this information is telling you. If you're a person that actually goes out and does testing, maintenance testing or commissioning on a transformer, you have to understand what this nameplate is telling you. Okay, so what information do we look at in the nameplate for setting a differential element? Well, we look at the transformer rating, 100 MVA. We look at the high side voltage. We look at the low side voltage. We look at the vector group, so we know how to compensate for that phase shift. And we use the primary and secondary CT ratios to set the differential relay. And how do we use that information? Well, it's quite simple. Here is the setting for the Beckwith relay. And I used to kind of like Beckwith relays. Their software is very intuitive and it's very easy to set. For instance, if we look at the same YD1 transformer, okay, we've got a VABY, we've got a Y connected primary winding, we've got a delta connected on the secondary, and AB would indicate that we've got an additional 30 degrees phase shift. Okay, now down here, we've set our CT ratios for winding 1 and winding 2. Okay, so with that information, what we can do is actually calculate what our tap setting should be. So for a tap winding 1, okay, and this is important because with the Beckwith relay, you have to do this manually. You have to run this formula because the taps are set manually. Okay, so basically we're going to look at the tap setting will be the MVA rating times 10 to the power of 3. That just gives VA with all of the zeros following it, divided by the square root of 3 of your high side line-to-line voltage in kV times the CT ratio. So if we look at the example here, we've got 100 times 1,000 divided by 1.732, which is the square root of 3, divided by 132 divided by 200, which is our CT ratio, and that gives us a 2.19 tap setting on the primary side. You run the same formula for winding 2, and these will be your tap settings. Now, if we go back to the electromechanical days, this is also similar to taking a BD or an HU relay and moving those tap posts into the right position. And what that does is that makes everything equal in terms of what the relay is seeing. Okay, so the tap settings are very important. Now, we can make quite a few errors here. If we say we invert the CT ratios on the primary and secondary side, you're going to have a problem. If we don't put in the right voltage levels, if we don't put in, the right configuration in terms of how the transformer is connected. Okay, so this is very important to pay attention to. So what we see here in the differential setting, we have a minimum pickup of 0.5 per unit. And I'll explain that when we look at the slopes. The slope setting 1, slope setting 2, and a slope point break. Okay, and then a second harmonic restraint and an output that goes to the main trip contact of the relay. So this is all fairly simple and very intuitive. If we look at the Schweitzer, it's a little bit different. Okay. Again, we see the MVA rating. We see how you've got a Y connected primary with a CT ratio of 200 to 1. Okay, and then and then the voltage level, and then we go to winding 2, which is Y connected. Okay, it's got a compensation of 1, which actually equates to 30 degrees, a CT ratio of 500, and the secondary winding voltages as well. So we will say that we enabled this element. And the thing about the Schweitzer is once you put this information in, okay, your tap settings will automatically be configured. Okay, and that's the big difference between the two. Now, most all of your modern digital relays for transformers has this auto tap calculation. Okay, but just one little mistake in the information over here on the left-hand side will change these values, and that will give you bad settings. So this is it's simple if you take your time, and that's the big thing. You can't be in a rush. The other problem that I run into is you have two groups of people. You have protection engineers that are actually putting the settings into the relay, and you've got a substation crew that's actually going out and testing and validating those settings in the relay. So if you're testing it, you have to actually rely heavily on the fact that the engineer put those into the relay properly or properly configured the file that you're going to upload to the relay with these settings in there. So that's, you have to understand that relay testing people, whether you're an engineer or a relay technician, you have to have as much knowledge as you possibly can because you're the last line of defense to make sure that thing's going to work. Trip logic, okay, is very, very important, especially with the Schweitzer. Now, with the Beckwith, it was easy. We just checked a box. It said, go to output 1. With a Schweitzer, you have to, yes, say it's going out to a certain protective function, but it has to be part of the trip logic equation. And this can be a little bit complex. You can actually enable the element, but forget to output it to a contact, whether it's an alarm or an alarm and a trip or just a trip. So it's important to make sure that these are doing properly. Now let's talk about the dual slope setting that you see on the differential. Now, a lot of people would ask me that aren't familiar with differential protection, why can't you just put a set of overcurrent relays? Well, you could, okay, but that would be just a one static setting, and it wouldn't account for things like CT errors. Okay, protection class CTs are only good up to 10%. So if it's not right on the money, okay, with just overcurrent relays, you're going to have a nuisance trip, and that's why we apply what we call a restraint slope, okay, to the settings. And slope 2, you'll notice that slope 1 is at one level, slope 2 is at another, and slope 2 is there to increase the restraint of the differential element. Okay, so that if you get a through fault from a transient and it causes the CTs to start to saturate, that will add additional restraint to decrease the sensitivity of the 87 element so it won't misoperate. And it looks like this. So this is your restraining region right here, and this is your first 25% slope, and here's where it goes to the second slope, which is 60%. Okay, so this is going to keep your differential relay from nuisance tripping if you have CT saturation or the CTs just aren't that accurate. But once that differential is high enough to indicate that you have a problem internal to the transformer, this is going to be your trip zone up in this region right here. Now, let's talk a little bit about second and fourth harmonic restraint and harmonic blocking. One of the phenomena that happens when you energize a transformer is that you're pushing current into the transformer, but it's not coming out yet. So if you don't block the 87 element from tripping one way or another, it's going to nuisance trip as soon as you energize that transformer. So to keep from that happening, They set a what's called a harmonic restraint. And what happens when you energize a transformer is you have a certain amount of harmonics, let's say 20-25% harmonic component of that waveform in both the second and the fourth harmonic restraint. Now, we use these words restraint and blocking kind of, you know, kind of like the same thing, but it really isn't, because if you're blocking the element totally, okay, what's going to happen is that if you actually close in or energize a transformer and there's already a fault that exists, okay, you're going to create an even bigger problem because you're energizing a transformer that's got a fault in it. Okay, so restraint means what we're going to do is we're just going to move the slope, the restraint slope up higher and desensitize it if we see a certain amount of second and fourth harmonic in that initial waveform. And this is what it looks like right here. This one was set at 20%. And you'll see that if we have greater than 20% harmonic component, this is your restraint region. If it's less than 20%, okay, that means that you're just operating under normal circumstances. You have a fault in the transformer, and the 87 element is going to trip. Now, there's a couple of things that you have to be careful of, especially with new transformers, because traditionally what you'll see is that, you know, whether you had a BDD relay or an HU relay or the old electromechanicals, they were kind of set statically at 20% or 25%. Okay, because that's normally what you'd see in transformers. Well, what we find that new transformers use a high flux density core materials, and that results in lower levels of second harmonic current during the energization. So that makes your harmonic restraint setting less effective. You have ultrasaturation, which is a phenomenon where the core is deeply saturated during the inrush, and that can lead to also very low harmonic content. And that means basically what we're seeing here is that with the new materials in some of your core and shell form transformers are actually giving off a much lower harmonics. And the reason I bring this up is because what that means is that your traditional setting of 25% isn't going to be applicable anymore. You may have to go all the way down to 8 or 10 or 12%. How do you know what kind of harmonics you're going to see? Well, the best way is to energize the transformer and then capture the waveform and analyze the waveform to see exactly how much harmonics is being generated during that inrush. And that will help you with your setting. Otherwise, if you just put it at 20%, you may see a nuisance trip. Now, there's a bunch of different ways to set a harmonic restraint. It's per phase, and that, and in that case, the relay performs a restraint on any of the three phases. 2 out of 3 means that it must restrain if it sees 2 out of 3 phases. And then some relays will do an averaging. In that averaging mode, the first relay calculates the second harmonic ratio and then applies the inrush threshold to a calculated average. In 1 out of 3 mode, all 3 phases are restrained when a blocking condition exists for only any one phase. So 1 out of 3 mode typically reverts to per phase mode after a short time delay, and that will allow tripping. And basically, it can be done either way, and that's a good an important thing to realize, that these are all settings in the relay, and this right here will help define what those settings mean. And it's always a good idea to refer to your protective relay manual to find out. Now, what common mistakes do we see when we're setting the 87 element? Well, one couple of things you want to look for. Number one is if you're swapping out CT ratios between the windings. Okay, and that's easy to do if you're not carefully looking at that nameplate data. So that's one thing I've seen. The other is not accounting for a delta connected CT. Now, a delta connected CT is sometimes there when you've gone from, let's say, an electromechanical relay to a digital relay, and you don't want to add another CT to the system. So you just have to account for the fact that that's a delta connected CT. Well, what does that do to your calculation for the tap setting? Well, it's going to incorporate that times the square root of 3 formula into the tap setting calculation. So you have to be able to make sure the relay is set to accommodate a delta connected CT. Swapping the voltages between the two windings, okay? Leaving the settings, and I've seen this all the time. People will go in, test a relay, put it in service, energize the transformer, and it immediately trips because they left it with factory settings. And I'll tell you this, 100% of the time, factory settings are not going to equate to the right settings that you need, okay? And that may be some of the settings, it may be all of the settings. And it could be that you thought that the engineer put the settings in the relay properly, but he didn't, or you may have a file that didn't get, that got corrupted when you tried to write that file into the settings program. So that's one of the things. Wrong transformer configuration. If you try and configure a DY11 on a DY1, you're going to have a mismatch in the phase angles, and that's going to cause the differential to trip, to nuisance trip on you. Incorrect MVA ratings used to calculate the tap settings, not setting the correct second and fourth harmonic restraint values accordingly, and making sure they're energized. Incorrect mapping of elements to relay outputs. And this is a big one that you can get into trouble with especially with the Schweitzers, because they're a little bit more complex. You have to make sure, okay, that you map that. Not only do you activate that element, but you map it out to the correct contact as well. And the big one, not enabling your sequence of events or your oscillography for any of the elements, not just for the 87. And that's very, very important. That oscillography is going to help you with your analysis in the event that something happens. Okay, let's talk about testing. The very first thing I do, okay, is I do what's called a sanity check. I'll take my test set, whether you've got a Doble, Omicron, or Manta, or whatever kind. To properly test a differential element, you need 6 phases of current. You can't just do it with 3. If you have 3 phases, the best you're going to do is minimum pickup, and you have to swap your test leads. So make sure you have the right equipment to test these relays. So what you're going to see right here is you're going to see the tap setting value on the primary side, and it's 180 degrees out. And then on your secondary side, the tap settings that are calculated there, and that minus 30 accounts for the DY1, okay? If you don't have these phase angles properly configured in your test set, the relay is just going to trip no matter what values you put on there, all right? So what do we do here? Well, we want to validate, first of all, that we have the test set wired properly to the relay. And then we want to make sure that it's configured properly, okay? So basically what you see here in the metering screen, and this comes from the Beckwith relay, and you see the same thing with the metering values from Schweitzer, is that I've got my winding 1 currents, my winding 2 currents, okay? And what I'm looking for to make sure everything's wired properly is all positive sequence currents on both the primary and the secondary winding. Okay, and you'll notice that I apply these values. I'm not tripping the relay. I don't get any outputs activated. Well, that's good, because that's not what you want to. That's what you want to have happen. This is like just a simple basic wiring check, the sanity check, I call it, to make sure that everything's wired properly. Now, let's say if I've rolled phase A and B on the secondary winding. Okay, let's say that I just put my test leads on the wrong phases. What you're going to see here is we go from positive sequence to negative sequence values. Okay, so that would indicate that I've got the test set wired improperly. And also what you're going to see is you're going to see the relay pickup. So you see that now these pickups are activated. I would say most definitely that this will cause your differential to trip. Because remember, the differential not only operates on the current values that it's seeing, but it's also looking at the phase angle as well. So if your relay is configured wrong or your wiring's wrong, that 87 is going to nuisance trip on you. Okay, so what do we do next to test the element? Well, the next thing is going to be, we're going to check the minimum pickup. And remember, our minimum pickup settings was 0.5. Okay, now that's not 0.5 amps. That's 0.5 per unit, okay, of differential. So what that means is if tap winding 1 is at 2.187 amps times 0.5, our minimum pickup should be 1.09 amps. So we're going to put the secondary windings at 0 and just ramp up our current until the relay trips, and that's exactly what it should trip at. Okay, that's the minimum pickup. And we do the same thing on winding 2. And this is no different than we did on our VDD or in our HU. Okay, it's just that it's 3-phase, not single phase. So you have to make sure you ramp all 3 phases simultaneously as you're doing this minimum pickup test. So that will verify the minimum pickup. Now, to verify, okay, the slope setting, okay, basically we can go to our metering screen right here, which is really nice on the Beckwith relay, and they have the same, I believe, in the Schweitzer, and just start to increase one of the phases until we get to this intersection right here and see the relay trip. So it'll plot it right on this line. Okay, so we want to check the slope, both the 25% and the 60% slope, to make sure, and then you can calculate the delta between the 2 windings to validate that the slope is set properly. Okay, so how do we verify our 20% harmonic? Now this is kind of tricky because we have to do one winding at a time. What we do is we superimpose frequencies of all 3 phases. So we're going to move our 3-phase test leads from winding 2 to winding 1. We're going to leave the actual, so now we've got 2 sets of test leads going to winding 1. So if it's set at 20%, okay, what we're going to do is we're checking for we're going to look at our second harmonic. So a second harmonic would mean that we're going to have in this test lead 120 hertz. Fourth would be 240. Okay, so a second harmonic component is 120 hertz. So we set this set of test leads to 120 hertz, and we start to ramp it up. Okay, and at 20%, 4.37, okay, which is our tap setting for winding 1, it should drop out at 0.874 amps. Okay, so if we start with 0 right here, it's not seeing any harmonics, it's going to trip. So we're going to ramp up this current in milliamps until it drops out, and it should drop out. That means we have a second harmonic component greater, okay, than 20%, and that will keep the differential from operating. And you do the same thing for if you have a fourth harmonic restraint enabled as well. Second is usually primarily what they use. Adding the fourth harmonic restraint just adds a little bit more security to the restraint on that element itself. Now, one thing I want to talk about is volts per hertz or overexcitation protection, and I think this is one that gets misunderstood very easily. Okay, volts per hertz is a relationship of voltage to current. Okay, it's not a voltage element, it's not a frequency element, it's a combination of both. So generally where we see this enables is on a generator. Okay, but not always. Okay, it could be on a EHV or a high voltage substation. You could have volts per hertz energized as well, and I'll get into that in just a second. But basically, it's looking at the difference and the difference between the percentage difference between the voltage and the current. So in this setting right here, what we have is we have a pickup of 110%. So if our voltage and frequency has a difference of 10%, okay, or 10%, after 360 cycles, it's going to trip. Okay, so what causes this? Well, overexcitation is different from overvoltage because overall voltage protection reacts to dielectric limits, okay? And this could be due to lightning strikes or overhead transmission lines, circuit breaker switching operations, anywhere where your voltage is going to spike. That's going to create a problem in the insulating system of the transformer and actually put a hole in the insulation. But overexcitation is different. It's protecting against what we call overfluxing. Okay, tough word to say. Be careful how you say it. But overfluxing basically causes heating in the transformer. And the voltage excursion may be less than the prohibited limit dielectric limits, okay, of an overvoltage limit. So the excess current causes excess heating, which will cumulatively damage the asset. And if it's left there long enough, it could actually result in a catastrophic failure. Well, how does this happen? Well, one of the reasons you see this setting, volts per hertz, on a GSU is because it's an event that happens to the generator when it is direct connected to the transformer. And with large generating stations, basically you have your generator, you have the transformer connected to the generator, and then you have your main breaker. Okay, so as basically a volts per hertz condition is a reaction to your AVR or your automatic voltage regulator having some kind of an issue, okay, where it's preventing the overexcitation is growing because the frequency and the voltage aren't coming up to speed concurrently. Okay, one's running away from the other. So this could be a problem. Now, there's an overexcitation limiter in most large generators that prevents the AVR from trying to supply more excitation current than the excitation system can supply. But these systems can fail. I mean, one of the definitions of what protective relays do is that they're there when systems fail. And this is one of the things that happens. Because remember, whatever happens with the generator that's directly connected to the transformer is also happening to the transformer. So if you have a volts per hertz condition or overexcitation in the generator, it's also going to create a problem for the transformer as well. So AVR protection in a generator comes in two forms: loss of field protection, which is for underexcited conditions, okay, because that can be damaging as well, but overexcitation protection for these conditions that we're going to set in the transformer relay itself. Now, one of the things that the points that I want to make is you can have overexcitation conditions in EHV or in a transmission system. Okay, and what would cause that? Well, generator load rejection. Okay, on a large scale electrical equipment failure or a large area line failure and power failure, basically the generating capacity of the generator in the plant exceeds what is being used. Okay, and the power plant at that point is required to reduce the generating capacity to that value, which is corresponding. But since the voltage and frequency fluctuations happen so fast, the power plants may not be able to respond fast enough, and you can have an overexcitation event. Okay, power system islanding. Okay, when you have major system disturbances, uncontrolled separation from the power system could take place, and that'll lead to further network stability. Downstream breaker failure creates a Ferranti effect, and that occurs because of light load or an open circuit at the receiving end. So Ferranti effect is basically due to the charging current in the line that can result in voltage or overexcitation conditions. Capacitors and reactors. Okay, when capacitors are off when they should be on, reactors are on when they should be off, can also create voltage fluctuations and runaway LTCs. Now we think of this, okay, as primarily a overvoltage reaction, not necessarily, and that's true. Your overvoltage protection should keep this from happening. But if at the same time these voltage events happen or these transients happen, and you have frequency fluctuation or a drop in frequency, you're going to have an overexcitation condition. So it's good to have a discussion with your relay engineers to perhaps involve or enable volts per hertz protection, not just for generators GSUs, but also for your transmission line protection as well. So this is kind of what the protection curve looks like. It kind of looks like an overcurrent relay where you have your percentage of volts per hertz and your operating time in minutes. And you can see that you have one for the transformer, you have one for the generator, and then you have your actual relay setting that you're going to apply that will protect both generator and transformer. And one of the things that's important here is that NERC tells us that, yes, we must disconnect. Okay, we want to protect our equipment, but they also tell us we want you to stay online if it's just a transient that's not going to damage any equipment. And that's why these inverse time characteristics are applied. We don't want a definite time to say, oops, I see I'm over my volts per hertz rating, I've got to trip immediately. That's not how it's going to work. It's going to see that and then start a timer. And then if it stays around long enough to cause a problem, then it's going to disconnect, because there's a lot of transients that go out on the system that can cause the volts per hertz to react. Okay, but we want to make sure that if it's not going to damage the equipment, we don't want to disconnect. Remember, that's the stability and the security part of what relays do, to not trip when they're not supposed to. So a typical setting, let's say, would be at 1.5% difference between the voltage and the frequency. Okay, it may want to set an alarm so you can just take a look and see what's going on if you have a problem with your AVR system. And then as the volts per hertz value increases, you want to apply you can have either a definite time setting, or you can have that inverse time characteristic as well. But the volts per hertz capability of a step-up transformer connected to the terminals of the generator, have to be considered during the review of this coordination. It's got to be very carefully calculated. And your protective relay manual will help you do this. Now, just a couple of guidelines. For transformer protection for volts per hertz, there was a new IEEE guideline. In fact, I was secretary on this working group, because the old volts per hertz curves were back in the 50s and done by GE, and they haven't been looked at ever since. And what we found was that the new designs on some of the newer transformers had a much higher thermal capability and thermal rating than some of your older transformers. So the curves have been updated in C57107, and that's a good guide to help you put this setting in properly. But typically the capability of the generator is less than that of the GSU, but not always. Okay, it depends on the age and the type of transformer that you have. And for the GSU, voltage and frequency protection also needs to be coordinated, because you want to make sure that your voltage and frequency elements are properly set, but they should be outside the setting of the volts per hertz element. And also your volts per hertz setting should be greater than 30 cycles. I'd say 30 cycles is probably the minimum to avoid a misoperation. Okay, the other thing is, and this is important, since volts per hertz protection has to protect the transformer and the generator while the generator is coming up to speed, it has to operate at 10 hertz. Okay, so anywhere between 10 and 60 hertz, that has to be enabled, because the voltage and the frequency needs to be proportional as that generator is coming up to speed. And this is what an oscillography would look like in volts per hertz. And you'll see the voltage starting to increase, the frequency starting to come down, and you'll see, this is right when you see the transformer magnetizing current. Okay, so the one thing that I want to point out here, okay, is that a volts per hertz condition can cause the differential element to trip. Okay, and the problem is the volts per hertz condition may not be high enough, okay, to actually trip on overexcitation on that element, but it may be enough to trip the 87 element. So what we see when we have a volts per hertz condition is we see a lot of fifth harmonic component in the waveform of the current. Okay. And this is a good thing to have happen because and I want to explain the difference between fifth harmonic restraint and volts per hertz protection, because when you have a volts per hertz protection element enabled for the transformer, you also want to enable a fifth harmonic restraint, because you may have enough volts per hertz condition to set off the differential without actually having enough volts per hertz to trip that protective element. So a smallest inclusion of a volts per hertz condition will generate this fifth harmonic. And that's why we need to enable the fifth harmonic restraint, so we don't trip, okay, from just a quick overexcitation event that's not going to do any damage. Okay, so that's the difference between fifth harmonic current and volts per hertz protection. A lot of people get confused as to what the fifth harmonic current is there for, or that fifth harmonic restraint. And that's exactly what it's there for, to keep the differential from tripping should you have a small overexcitation event. So overexcitation can cause the 87 element to trip, and for that purpose, we use fifth harmonic restraint, and we issue a blocking for the differential element as if a single phase fault or two phase fault occurs in the transformer, and one phase remains unfaulted. The differential element's going to remain blocked, okay? Or restraint. I should use that terminology. Okay, so that improves our strategy. Basically, what we do, instead of blocking the whole differential, we're going to just again raise the restraint value. Okay, because let's say what happens. Let's say you have a fifth harmonic blocking going on because of a volts per hertz condition, and at the same time you have a fault internal to the transformer. Okay, so it's a little convoluted, and I don't know if it's ever really happened, but if it did happen, we'll still have some protection in the higher restraint area up here. So common mistakes when testing, and this is really, I think, pretty important, because I've seen this a lot, and I'll give you an example. We were out on again at a nuclear facility, doing a commissioning test on a transformer differential element. And when I went and I went to the nameplate and I configured all I looked at all my settings, or looked at all my test values that I was putting in, the relay was tripping. And I turned to the utility technician and I said, this thing isn't testing correctly. He said, we tested it on the bench. We tested it with everything was fine. And I said, how did you test it? Well, we tested it with the software that we use that takes the settings out of the relay, configures the test, and then applies the right values. I said, okay, well, we better go into the relay and look at the settings. And sure enough, they had rolled the CT values. Okay, so my point is this: if you don't validate the settings in the relay and somebody makes a mistake in putting in the wrong values, the relay is going to fail. Okay, so a couple of common things when you're testing relays that I think are really important. Number one, don't change the settings just for testing purposes, and I saw this on the old electromechanicals. They'd be doing a BDD or an HU relay, and they'd put the tap values on 1 amp or put them on 5 amps and test the slope that way, because nobody wanted to do the math to apply the right per unit values. Well, this happened at Dow Chemical many years ago, and the guy took the HU out of service, moved the taps, tested the relay, put it back into the rack, closed in the CTs, PTs, and trip contacts, and took the substation out of service because he forgot to put the taps back. Okay, so don't go changing your settings. Don't change the logic that will affect the relay's operation when in service. Okay, keep the logic as it will be in service. Keep all your settings and all your logic as it's going to be installed when you're doing your testing. Incorrect wiring of inputs, rolled phase, reverse polarity. I get calls all the time, people doing their distance element. Hey, it's going in the wrong direction. I said, you got a rolled phase. Don't assume that the settings in the relay are valid, either the set points or the logic. select the appropriate logic for binary IOs. Okay. Make sure if it's a Form A that you're looking at a Form A. If it's a Form B, make sure you're looking at Form B. Not validating that your sequence of events, your target indicators, your fault monitor, your fault or your through fault monitor are set up. If you test them, okay, if you create a fault, go in and look at these different files to make sure you have them set properly. And another one, don't test a relay with factory settings. That just doesn't make sense. Even if you're just doing kind of an assessment test on a new relay that you're thinking on standardizing in, don't test the factory settings. Put real live settings in that would actually apply to where the relay is going to be installed. Okay, there are others. If you can think of others, certainly just let me know. But these are the most common ones that I see during the testing process. All right, Randy, we're all set now. If anybody has any questions.
Okay, thanks. Okay, good presentation, Drew. Every time you speak, I learn so much from your presentations.
Thank you.
Yeah, you're a real font of knowledge. Okay, couple of them here. How do SCL 787 and Beckwith M3311 differ in their approach to differential protection?
Well, the biggest difference is in the auto tap setting. And that is really the biggest. I mean, with the Beckwith, you have to calculate those taps. And something I'm not really opposed to because it gives you that education. Where did these tap settings come from? You know, to actually help you.
Well,
and you have to interrogate the nameplate. But that's
really
the
next question. What's the most common nameplate detail that technicians misinterpret when calculating tap settings?
Any one of them. And I'd say the most common is how the transformer is configured. The delta Y1 is one of them. Is it a DY1 or is it a DY11? That's probably the transformer configuration is probably one of the most challenging in terms of being able to interpret and apply properly. And incidentally, and that's a very good question, because if you're testing the relay from the test switches that are in the panel itself, you're only testing the wiring from the test switch to the relay. If you've rolled a CT or if you've wired it wrong from the CT secondaries down to the terminal strips, it's going to nuisance trip. And you'll have to look at your oscillography to see which phase is improperly wired and which winding.
Okay, what field conditions most often lead to CT saturation during through faults?
Well, that's just it. High through faults will
Right.
add CT saturation into the mix. Yeah. And this is a good reason why you want your through fault monitor enabled. So you can see the magnitude, the duration, and the number of occurrences that you've had in the relay itself. And not only can that tell you that you may be saturating the CT, but it will also help your maintenance crew define what type of tests they should perform when they go out and do maintenance testing on the transformer, because through faults can be very damaging to a transformer. It creates some mechanical damage. And the shock can actually cause problems with the windings itself, cause winding deformation. So enable that through fault monitor. I had a conversation with a guy from Schweitzer a number of years ago when I started talking about through faults and through fault monitoring. He said, he was a transformer relay expert, and he's been out in the field for many, many years. And he said, when he gets on site, he said at least 70 to 80% of the relays don't have the through fault monitor enabled. And that's a shame.
What testing step do you see technicians skipping most often that leads to relay misoperation?
I think in general, I see that we don't pay enough attention to logic. Because there are supervisory inputs in a relay that enable the element that may get overlooked. I see people taking shortcuts a lot of times. This software that will supposedly automatically extract settings from the relay and then maybe, disable or enable elements automatically so you don't get interfering results. I, 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 I frown on that a bit. I think it's a
Right.
bit of a crutch, sometimes needed, understandable, because these relays can get very complex. But do your best not to change the logic,
Mm-hmm.
because if you forget to enable something that you disabled for the testing process, you're going to run into problems down the field eventually.
I don't know whether you heard or not my questions to Alan about AI, but I'm talking to Brian Sparling, I'm talking to you, I'm talking to everybody
Uh-huh.
these days about how it can be. What are the opportunities for this? So here's a couple of questions.
Sure.
How do you see AI helping technicians detect setting errors before commissioning, especially with complex differential protection schemes?
Yep. Yeah, I think just a collection of data and accessible to that collection of data, for relays that have misoperated, and
Hmm.
for technicians to be aware of what that misoperation was. Now, it's interesting you brought that up because I've been on the IEEE Transformers Committee now for, probably 8 or 9 years, active member for 6 of those. But the one thing I always wanted to do was get a standard for a nameplate on a transformer to have a QR code. And in
Hmm.
that QR code, it would be a standard format that all transformer OEMs would use, where you could actually use that QR code to input all your settings for
Hmm.
the transformer, and then to also define how you're going to do maintenance testing on that transformer, because all that
Good
nameplate
idea.
data is easy to
Yeah.
misinterpret. So, that's one thing that AI could certainly help us with. But we all know that with digital relays, 30 to 40% of misoperations come from incorrect settings. Another
Mhm.
20 to 30 come from incorrect logic.
Okay. So if it can help with that, great. Do you
Mm.
envision AI being able to correlate relay event reports, load history, and transformer aging data to forecast emerging risks?
Oh, absolutely. Yeah.
Uh-huh.
I mean, especially with through fault monitoring, because the more through faults you have, the greater the magnitude, the longer the duration, the more likelihood that it's a cumulative issue that will eventually lead to the weakening of the structure of the transformer. So, having data on, if I know that my transformer has a certain rating, a certain age, and it's had a certain number of through fault occurrences, what is the likelihood that I have incorporated or incurred some type of mechanical damage?
What role will AI play in dissolved gas analysis?
Um, well, again, I think DGA is a great tool in trying to determine if you've got an issue inside the transformer. What I think people may not be able to interpret is, what are those results telling me? So I think that the chemist that's doing the analysis and the professionals that give you recommendations, um, if we had historical analysis on, if we had you know analysis on transformer faults, when we break it down and we look at what the fault was and correlate that to what the GGA was telling us, and had an international database of this, what levels of gases, what types of gases, and when we did forensics on the transformer, here's exactly what we found. So I think this would go a long way in helping field technicians interpret. And that's the
Where
hardest part,
where
is
where would
interpreting
that where
results.
would that database be stored? Who would run that?
um, that's a very good question. I think that's something that some of our governing bodies ought to be
Yeah,
involved in.
like C Gray or IEEE or
Oh
like
yeah,
that, right?
absolutely. Yep. Or
Maybe
even
that's,
NERC.
yeah. Okay, good
you
idea.
know,
All right. Okay, those are the questions. Great. Thank you very much. I appreciate your continued support for these live online forums.
You bet,
And
Randolph.
yeah, thank you very much. Okay, so everyone, that's our 4 presentations for today. We appreciate your hanging in there, and we look forward to seeing you again. We have a new schedule coming up in 2026 of live online forums. You can go to